Yeah. I assume the reason they're not
that's why people don't listen about it.
Yeah. Basically, I mean, it's not gonna take a long time to have this. So, just like it's all and now it's
I did hear. Yeah, right.
I mean, everything looks, you lose all sense of color.
And it's also.
So he'll still wide.
And most of the.
We're shining down.
Yeah. Plus, you know, pick the right person.
Yeah.
And people don't understand about it.
I mean, is that for your health and circadian rhythm?
Well, for everything.
Yeah.
If you pick a higher temperature, there's more food.
Right. But does it help us from you guys that we're.
You know, I'm sorry.
I just started.
Oh, I don't know that. I'll have to ask.
Connie, you're gonna have to help me if you're introducing your husband.
You know, like.
Dr. Chris Walker, is a full professor at the
How free to come.
Wow.
So.
I'll be up here with you.
You know, it's still very nice.
I would imagine it would be.
Less of shot when you go outside.
Yeah.
So there's less.
Astronomy.
They have, I think 65 to 27 times. So it's the whole tunable light. So, when you want recommendation, that's probably the next step you want. You turn on both. Yeah, that's really good. Color better. I mean, it's clear.
Wow.
You just turn off the icon. Like this is not my bad, but
I wouldn't imagine you putting anyone that, so that's right. That's great.
Well, I
I
told
bet.
Jordan, like, when I was in.
Am I saying that on air already?
Yeah, you're in my spot. That's cool.
Cool.
Yeah.
That's right.
Sorry about that.
No problem.
Are we, about ready? Yeah. Okay. Okay, normally we have a giant applause track or something, but yay! Woo! Okay, so we're resuming our schedule for the second part of day 2 of the Arizona Dark Sky Star Party, sponsored by Oracle State Park and Explore Scientific and the Explore Alliance. David Levy headlines this event. He could not be with us in person today, but he was live with us over Zoom today, so it was great, and we're glad he made that sacrifice. Today we have Connie Walker with us. Connie is, I always knew her from the NOAO, but they changed their name, right, to NOIRLab. And so, but I think she does a lot of the same stuff. She's a powerhouse of educational outreach, known all over the world, all over the United States for the work that she's done. I've known her for 15 years at least. Yeah, I think the first time I got to meet you was at an AAS meeting in St. Louis, Missouri. So, yeah, so, and Connie has been, I think physically has been to University of Arkansas in our neck of the woods in Northwest Arkansas. But this is where she lives. She's from Tucson, and so really pleased to have her today. I'm going to turn it over to you. Thank you.
Thank you very much.
Thank you. Yeah.
I just want to give a shout out to David Levy because he was actually one of the first people that ever recognized I did something good for educational astronomy, for the astronomy education. And he actually named an asteroid,
Oh,
which was totally freaking amazing. I told him that was the best thing since the birth of my kids. So anyway, I just want to give a shout out to David and thank you very much. I wish I could have seen you in person. So today I'm so pleased to be here with you guys because actually I'm changing gears a little bit in terms of my vocation. I'm doing something slightly different and I'll tell you about it. It has to do with light pollution still. I've done a lot of light pollution for the last 15, 16, I think actually 17 years now. But it's moving into the realm of not just light pollution from the ground, light pollution from satellites, not light pollution from space, believe it or not. So today I'm going to talk to you about light pollution from satellites, what should concern us, and why you should be concerned actually too. So as I said, I am a scientist at the US. It's a national center for optical astronomy, and it is called, a funny name, NOIRLab. I am co-directing now a center for the satellite constellation stuff. It has a long name, and I'll only repeat it once because it's so long. It's called the Center for actually it's the International Astronomical Union's Center for the Protection of Dark Applied Sky from Satellite Constellation Interference. And if you can say that 10 times fast, you all win a prize. So we call it IAU-CPS for short. And this is a topic and a concern that is really drawing in more and more people steadily because it's becoming such an important topic to deal with. And we'll go over what I mean by that. So essentially, we're entering a new era. Oh, we want to go to the next slide. Sorry. Next slide. Thank you. So this is a silly graph here, but I'll tell you all about it in just a second. But first, let's pay attention to the first two panels on the left-hand side there, one from 2021 and one from 2028. We're actually, it's showing how we're entering a new era of Earth's orbital space environment. The illustrations here show the number of low Earth orbit satellites, commercial satellites, that were actually in orbit in 2021 last year versus what's projected because of all the filings they have now with something called the Federal Communications Commission and also another international one called the International Telecommunications Union. Those two things are very important to file all of your launches with. And right now there are actually over 100,000, really more like 400,000, honest with you. Because recently Rwanda asked to be able to launch 327,000 satellites. Now that was by the co-founder, the ex-co-founder of OneWeb. So he knows what he's doing, guys, and I'm afraid that might happen, but we still don't know just yet. So we might be looking anywhere between 100,000 and 400,000 satellites up there. And again, not all of these may actually launch, but there'll be quite a few. And this is a quickly developing area. And it's not just one player, it's many players. They have a lot to contend with here. Oh, I should tell you the other plot. You want to pay attention to that blue, that neon blue curve at the very bottom, because until about 2019 or so, it was just steadily increasing at a somewhat linear rate. And suddenly with the launch of the Starlink satellites in May of 2019, and many others followed, it exponentially increased pretty dramatically. But let's go to the next slide, please. So here's a set of, just to get you fired up here, here's a set of street images from various ground-based observatories around the world. This is more and more what observational astronomers, whether they be amateur or professional astronomers, are seeing when they go to the telescope to try to get observations for their science. And just to give you a view. Let's go to the next slide, please. this, okay, so street so what you're seeing here actually is a graphic of the sun on the left and the earth is the blue, with people standing on various times of the day and night. And then the two yellow circles there are actually one low Earth orbit satellite that is close to the Earth, as you can see, and one is further out. And what you want to notice is actually that little red cone that is the Earth on the opposite side of the Earth from the sun. You'll see that that's where it's supposed to be Earth's shadow. And once a satellite goes into that part of that cone, it'll be very difficult to see, right? And that's kind of good. But as you'll see that as you go higher in altitude, there's less and less chance to be in that cone. So that's something I want you to remember during this talk, okay? So, all right. So as I mentioned, we have a hugely increasing rate. Oh, next slide. I know this one was good. Thank you. You're on top of it.
I saw your
You're on
finger.
top of it. We have a hugely increasing rate of new commercial satellites, and they appear most prevalent near twilight. And that's because they are reflecting sunlight, and we see them illuminated by the sun shortly after sunset and shortly before sunrise. And near the middle of the night, there's not quite as many reflecting sunlight unless they're at very high enough altitude, as I mentioned before. And then they don't fall into Earth's shadow. So basically, you can see the satellite streak almost any time during the night. It's just a little bit less that you see visibly. They're there. You just don't see them as visibly as you would at other times of the night. Okay, so this is going to impact an observatory I'll talk a little bit more about. It's up and coming and very, very cutting edge. It's called the Rubin Observatory. More on that later. This is an issue. For new satellites constantly launching, and the old ones constantly deorbiting. That's another thing that's happening. And to maintain this large population of satellites, you're going to have to continuously replenish them. So you're going to see, the lifetime is for about an average satellite is about 5 years. So you'll see them constantly rising and deorbiting, and it's going to become more and more because more people are starting to launch, and so you're going to see it quite more frequently than we have in the past. And so if you want to maintain those thousands of satellites, you're going to have to, you'll see how the numbers are going to increase drastically. They're going to be something. So that's, and then, you'll notice too, that when they are launching and when they're deorbiting, there's times when they're going to be really bright as well. They can't quite control the attitude as well of the satellite. So they're going to be very reflective. They can't control which side is going to be facing the Earth, which side is going to be reflective, and they're going to be coming closer and closer to you. So, so the plot on the left-hand side is kind of peculiar looking. You have, it's kind of hard to see on the screen. I apologize. On the bottom, you have sort of altitude increasing to the right. That spike is the spike of the Starlink satellites at 550 kilometers. And you see that represented again in the upper panel, where you have a lot of high density of dots at the 550 mark, which again is representing Starlink satellites.
It's a solid line.
Yeah.
I mean, you can't probably see it there, but it's a solid line
Yeah, you
on the
can,
graph.
you can basically see it there, but yeah, you're absolutely correct. So that's the important part to that one. We can go to the next slide, I think. Let me see. So there's a Nature article. It's really kind of cool if you ever want to, and it's pre-readable. So it's by Lawrence and my colleague Meredith Rawls and Marie Jha and al, a bunch of people. And I think maybe John's on that paper. Not the one? Okay, not in 2000, this is a new one, just this last April. And it's a case for space environmentalism, because it's not just the astronomy you have to think about. We have to think about what we're doing to our environment. There's a lot of things I could go into them. I can't really in this talk go into everything, but it's a human environment and it's in need of preservation. So one main point that we need to consider is the cumulative effect of launching satellites and operating the satellites. And if you're launching only 50 today, no big deal, right? But if you're doing that every week and every month for years, you need to consider the cumulative effects. And it's analogous to considering the cumulative effects of carbon in the atmosphere. Building one new power plant isn't going to hurt anything. It's not going to totally ruin the Earth's atmosphere, but cumulatively, there's a real effect. And I think John might tell you sometime, if you haven't already this morning, about the effect it has if you have an aggregate number of these debris in the atmosphere. You're going to have a possibility of sky brightening at night. So John could tell you more about that. He's an expert in that. And for those online, it's John Barentine. Barentine. Okay, we can go to the next slide. Okay, so this is a cool movie I want you all to witness. This was made a few years back. I think I could, yeah, you can get it going there. And you'll notice it starts in 2017 with one of the first launches of the satellite there, and it exponentially increases as the years go by. And you'll see the paths. I hope you see the paths as it get more and more sort of densely populated and orbiting all these satellites orbiting the Earth until it becomes so opaque that it kind of is frightening. So it goes all the way to about 2029. We're almost there, but it's actually much thicker. So maybe we haven't seen it before that. But this lists everything that has been what's the word I'm looking for, John? Who's the FCC and who's the ITU?
They've licensed for
Licensed,
operation, but they may not have launched yet.
Thank you. Yeah, yeah. And so these are all that are planning to be launched. They have to state when they're going to be launched, but they might have not launched just yet. So there you go. Okay, next slide, please.
So, Connie, quick question about that.
Yeah.
From the scale there, it looks like there's becoming no space between the satellites, but obviously there's
No,
still some required separation.
That's the hard part to illustrate, because you're
Right.
absolutely right. Any good scientist would notice that. Thank
Yes.
you very much.
Yeah.
Yeah.
So, but they're still maintaining this several miles, but not several hundreds of miles separation.
Well, it can actually be sometimes closer than a mile. So, yeah, it's kind of frightening. There's been a number of maneuvers in space to avoid collisions already. Between, SpaceX and other satellites, between Russia and the United States. I mean, you name it, it's out there. You can find out all about this. So why should you be concerned about this? So I would say that you guys know better than anybody because you really appreciate the night sky. And all of us have stand in awe of the night sky at one time or another, maybe very frequently. So the sky is more than just the science we get out of it, right? And not only have we been stargazers, avid stargazers, but I'm sure our ancestors have been as well. But when we talk about the science, we don't know what we don't know. Okay, so we've got to maintain that edge to discover things. If we take away that opportunity to be able to discover things, the choices that we're making now are going to really affect our future in many ways. All right, we can go to the next slide. So I'd like to talk a little bit about the impact on a very up and coming cutting edge observatory that's coming online in early 2024. They've been building it for the last few years down in Chile on a mountain called Cerro, and it is so truly amazing, guys. You will not believe it. Let's go to the next slide. So the instrument on it, once he's ready, we can see the next slide. Yeah, the middle thing there is you can see the size of a person there behind the railing. I mean, this thing is gigantic, right? It's a camera. It's a single camera. And it's called the Legacy Survey of Space and Time, or LSST. And it's part of the Rubin Observatory. It's going to be a 10-year survey, or one big 10-year movie. You can think about it. You don't just take static photographs. You're taking a continuous movie, and you can see things go, as they say, bump in the night, right? You can see things happening transiently. So they're going to map the whole sky every 3 nights. That's unbelievable, the whole southern sky. And the data and all the software will be available for the community. And they have science they're going to be doing from solar system science all the way through to dark energy. It's going to be very incredulous. Let's go to the next slide, please. So This software is going to enable some very real-time discoveries. They have an alert system that's unparalleled. They'll be able to get onto something within like a minute or less. It's going to be totally amazing. And they're hoping that they'll have 10 million nightly alerts. It'll take 20 terabytes of nightly data. And in 10 years, they are hoping, if everything goes well, to detect 20 billion new galaxies, 17 billion resolved stars, and 6 million solar system orbits. Isn't that pretty incredible? Think of what we're going to learn. But, next slide. There's just one problem. So it's estimated that if we do get 100,000 satellites up there all at once, that because of, well, there'll be probably one at least satellite per image. If you get 400,000, it'll be every image. We'll see at least one satellite. So you're talking about pixels that will be not usable. So a good fraction of the data will be lost, and that's an increase of time. Or if you can't think of ways to, I'll talk about all this, but ways to mask it or to avoid them, it's just going to be kind of difficult. Thank you for going there. You can stay there for a minute. Actually, you can run the, there's a little movie there, and yep. If you, there's a bar that pops up at the very bottom of the white window. Yeah, you got it. Perfect. It should go a little faster, but it's okay. It's the buffer, I guess. So as mentioned, Rubin Observatory will be an amazing 10-year movie, surveying the whole sky every 3 nights, and it has this awesome potential to do this wide field, very wide field of view, and very sensitive detectors to detect very faint objects. Those same features, however, are the very things that make it vulnerable to satellite streaks. You can run it again if you want. It's pretty cool. It's not showing up as well there. So this is the middle of the night, I think.
It's still running.
Okay, yeah, all right. So this is the middle of the night. You saw the beginning of the night that was on the, basically on the right-hand side, that big circle on the left. And now it's morning coming up. And this is all the satellite streaks that you're seeing. Morning. It's equally as bad at the beginning of the night. So you have twilight in the morning, and the first one was twilight in the evening. So that's basically what I was saying. But you see it, and that's going to be for the, that's I think just within, was it 10 minutes? No, it's a whole night there for that one. But that's the Rubin Observatory, and it's supposed to, it was projected for the middle of October, I think, this year, with all this, this is, I'm sorry, I have another simulation that's in October. This one is from Mariba Jai. He's at the University of Texas, and he did this 2 years ago when he had only the data that he knew to that point that had been listed or licensed with the FCC or the ITU. So it's pretty dramatic. Okay, so we can go to the next slide. Come on. Good. Okay. Another curve. I'm sorry about this, but this is the way that a scientist gets to convey that there's actually data out there to substantiate what I'm saying, basically. And that's why I'm showing this to you. So you saw the plot already on the right-hand side on that blue curve that I was mentioning to you of the active satellites and how they're increasing exponentially in the last few years. You can see it going up there starting in 2020, a little bit before 2020, actually. And that is corroborated by these observations that was taken by a facility that's much smaller than Rubin, but does the same sort of survey as Rubin does. Continual survey, as it's called the Zwicky Transit Facility, It's based in California at Mount Palomar, actually. So they took data, they looked at all their data for streaks, and they found what you see there, and it follows that exponential curve quite well, right? Unfortunately. So this is not some, simulation we're running here. This is the actual data. Right? Go to the next slide, please. So I think this might be the last of the movies that I have, but this really does give you a very good impression of what's going on when you're thinking about observing hazardous asteroids. And I think everybody agrees that we want to maintain watch over hazardous asteroids approaching the Earth. So there's pretty well-known astronomer, Siegfried Egel at the University of Illinois, who's working with Rubin Observatory. And he's looking at solar system discoveries. He's projecting how they're going to be affected by these streaks once he's observing on the Rubin telescope. And he and others in his field have noted that the new object discoveries of these hazardous asteroids require at least 6 detections over 3 nights. And if one of these is missed due to the streak, then you will not be able to discover the object at all. You need multiple observations traced together in an orbit to confirm detection. So near-Earth asteroids are a particular concern because they have very short discovery windows. And if you want to find something that might crash to the Earth, you have to have lots of, you have to have, and you have lots of satellite streaks and images, and you may not find as many or as soon as you might need to find them. Unfortunately, I'm laughing here. Should be laughing. Okay. So what are some other kinds of sciences that are impacted? And I just list 2 here. There are many. Cosmology is one of them. Cosmology really requires very faint detections. And if there's anything in its path like a streak, you've lost that capability to detect that particular area you want to do some cosmology on, basically. And spectroscopy, well, there's the solar spectrum that gets reflected. It might get reflected down into an instrument and might kind of compound itself with whatever you're observing. And you won't even know it sometimes that you have a solar spectrum in your data. So this is kind of the concerns they're facing. And I could list a few more, but that's the ones that are kind of important. Go to the next slide, please. Good, thank you. Now this one's very impressive for 2 reasons. There's 2 things going on here. The one on the left-hand side is a glint. Actually, that happens. You see what's happening is a satellite's going across the sky, and in the middle there you see it getting brighter, right? And it's getting brighter for a particular reason. But the graduate student, Harry Krantz at the University of Arizona, was taking this data. It's part of his thesis, and he was wondering, oh my gosh, what's happening here? What's different? And he called up SpaceX. He's a very gutsy little fellow, and he called up SpaceX, and they told him, oh my goodness, you're right. There was some sort of maneuver. And come to find out is one of these satellites, the Starlinks with a visor on it. The visor produces drag, and they didn't realize this when they put the visors on, So every 3 days, they have to maneuver the satellite to go higher in orbit. And when they do that, it doesn't orient itself as steadily as before. And you're getting these surfaces that are shining, glinting, and towards the Earth, right? And lots of data. Lots of bright spots or streaks. So anyways, that's the summary of that one, I think.
So the one on the right is the new one. Is this something?
Say it again, please.
What, the image on the right?
Now I get to tell you about this is let me see if I get this all right. AST Space Mobile Blue Walker 3. Is that right? Did I get that right? This is actually the prototype, the one that's actually going to be launched. I think it's 53 meters across. 53 meters across. Bigger than this thing here. It's like a tennis ball here. And they have all this white in there that doesn't have any coating on it at all. Any darkening, right? It's going to be horrible. Even this one. And we have people on our team that are starting to observe it all over the world, which is kind of a good thing to see what kind of data we're going to get.
What's the purpose of the satellite? It's an orbiting cell phone tower.
Yeah, and they shouldn't have the license to do this. It's against the rules, basically. But because this was framed as a prototype, they got away with it. There's a lot of things we're combating, guys, and we do need people's help. We can't do it. There's so many problems out there right now. You cannot believe it. And John can corroborate this with me. Anyway, so it's bad. It's gonna be. I think this one's gonna be at least 2nd magnitude in brightness. The other one, I think the big 53 meter one is going to be about the brightness of Vega, 0th magnitude.
Wow.
Yeah. And that's not the worst of it. They were asked by NASA to lower their orbits so it wouldn't conflict with, Hubble and ISS and stuff like that. So they went from, I don't know if it was like 700 down to maybe 400 kilometers or something. And in doing so, you must have more of these things. So instead of having a couple hundred at whatever it was, 700 kilometers or so, they now at maybe 340 kilometers are having a couple thousand. So imagine 53 meters across, a couple thousand of these things with the brightness of Vega polluting your sky, right? I say that it's really polluting your sky. So here we are. This is what we're going to contend with in the not so distant future. So I thought I'd just mention radio astronomy, give them one slide. So modern radio observatories need to observe not only in the protected bands that you see in yellow, and that's the narrow little things you see that they're allowed to have their observations in, but they also actually need the broader bands you see in blue. And to do this, the radio astronomers have historically relied on technical mitigations, especially in avoiding satellites, as well as locating the telescopes in what they call radio quiet zones. And radio quiet zones are in very remote areas typically, and they're protected typically. It's nice to have some regulations. They're protected by national legislation. That's good, but they have no influence on the satellites or the satellite companies. So those satellite companies, it's like the Wild West. So, I mean, there are some rules that they still have to follow. We have to say there are some rules that the satellite companies do follow, but there's still got some very big points of contingence. So the radio telescopes can see all the satellites above the horizon. You have these downlinks that are beaming down all the time from satellites. And before the occurrence of large constellations, most satellites were fixed in the night sky. They were geocentric, geostationary orbits. And you could, kind of know where they are and know how to avoid them. It was easier. Now that you have them going all over the place at any time, it's a lot more difficult for the radio observatories to actually, avoid them. So, quite the problem. That's what that slide is all about. So next slide. Oh, thank you. You're really good.
I'm catching your rhythm.
Yeah. When I slow down and stop talking, well, that's good.
No, just use sense.
Okay, so this is just a statement that at this point I like to make because it's pretty impactful. We had, and you'll learn about this in a few minutes, we saw this coming in 2019, we didn't see it coming. Our jaws dropped. All astronomers' jaws just kind of fell to the ground. And we were just so amazed. We got on the, I don't know what you would call it. We started doing something by 2020. We had organized ourselves to do 4 workshops, two in 2020, 2 in 2021. This is one of the quotes from the very first workshop. We had about 100 people, or at least 86 people working with us. And it was amazing, amazing, amazing effort. And they said, you know what, after all this studying we've done, we have to conclude that there's actually no combination of mitigations that can fully avoid the impacts of the satellite trails on the science programs of current and planned astronomical facilities. It's really a sad statement. We're going to try as best we can, but it's going to be a compromise. Right? We'll never have our skies the way they were. That's an unfortunate statement. Okay. Next slide, please. Okay, so we've identified this as a problem. Can we work around it? And here are some things I'll describe as what we're doing to try to work around it as best we can. So you may have heard, that SpaceX is working to make their satellites darker. And they did try with DarkSat, and that was like a coating that you can see it brought it down to 6.2 or something magnitude, so about a magnitude better than the previous satellites that were initially, I think they called them version 0.9 or something. So that was good, but that was not good enough. That we couldn't still take out the streaks totally from the images, right? Or at least the crosstalk, there's like more lines that are around the streaks. if they get saturated and stuff like that. So we couldn't fully subtract them just yet. And then they tried, and this is very good of them to try more, try another way. And it was something called VisorSat, which was a sun shield. And that brought it down a little bit more. So you can see the difference now. Instead of this way, is actually across. You have the before in the right hand image, you have the before on the left and the after on the right. So it was like magnitude and a half or so better. And so that was an improvement, but still it wasn't quite there. Okay. So the reality is that the satellites are still not dark enough. In addition, SpaceX is not the only operator. They have been a pretty good citizen, to be honest with you, and a good role model for other. There's another couple of big companies that are starting to respond to it in that way as well, that we're communicating with and doing things with. But there's no guarantee that all the other operators would follow their example. And at the moment, there are no regulations and no policies that require them to do so. It's all voluntary. So, I think that's good. Let's go on to the next one. So there is some work being done by the people at the Rubin Observatory to try to fix the streaks somewhat, not entirely. There's no magical way to erase the streaks completely. And unfortunately, you just can't Photoshop them out. I wish you could. However, by actually co-adding images, individual images, so you stack them basically, and not just looking at one image, you can much more easily mask the pixels that have the streaks in them. And then if the streak has a brightness less than 7th magnitude, this is done much more easily. You can't really totally mask it if it's brighter than 7th magnitude. So the limit of 7th magnitude makes streaks easier to deal with the Rubin data at least, because there's non-linear crosstalk that I started talking about earlier that happens if it's brighter than 7th magnitude. You get these lines on either side. I might have a picture of it in here somewhere. And that's called a non-linear crosstalk. And just to note too, because some people ask, and I have to throw this in, if you go to redder wavelengths, it's even more difficult they tend to be brighter, the streaks. So nobody has come up with a way of addressing that just yet, but we're all trying. So next slide. So how about avoiding satellites? Can we schedule them to avoid? And again, Rubin's doing a scheduler that's kind of pretty cool. So they have forecasting down the bottom there. They do it for Starlink, and they do it for OneWeb. So on the left is Starlink, on the right is OneWeb, and on the left you see those blue spheres. They're the distribution of the satellites. There's a lot of Starlinks, right, that are projected to be there. And then on the right hand side, that's OneWeb. There's less of those, but they're basically even brighter in some ways because they're not as much of a shadow. So this is something to watch for. Let's see. So, and of course, the forecasting is not highly accurate. So there's yellow-ish spheres that you see there are their scheduled program that shows you where you have to avoid. This is just in a particular moment in time because it changes. So the ones that are not as yellow are the areas they want you to avoid observing because there's so many satellites. And that, of course, is just for one satellite each. Imagine for everything. You can go next. Okay. Yeah. Thank you. Also, if I take too long on the slide, just go for it. Okay, so this is kind of hard to read, and I really apologize. I didn't really know the size of the screen and all, but I tried to make it as big as I could on the slide. This is a cool plot that a friend of mine with her collaborators, Meredith Rawls, had made, and she works for Rubin, but also the University of Washington, and she's head of one of the co-leads for one of our hubs in our center called Sat Hub, which you'll learn about shortly. But this shows you basically who, how can I say this now? Well, maybe I should start with this. Many operators, satellite operators, aim to provide worldwide broadband internet services, which is a real need. No one's going to, denounce that at all. But commercial satellite operators are not humanitarian missions. They're money makers, right? And large and bright satellites are going to cause harm. And so satellite internet remains unaffordable to the groups that are most in need of it. So those are in the lower right-hand side. See all those circles? Now, the open circles are the ones that for which ground-based service is cheaper. There's more of those than there are the solid ones, right? Right. And the ones that are blue are the ones that can afford it and are getting it, right? The ones that are above, I don't know how they define this, but they say they don't really need it, but they're getting the service, right? So, so that's the area. And there's about everyone has a name next to it. That's about 80% of our whole population around the world. Isn't that kind of cool? Of all the countries, circles are showing, I think, more than 50 million people in each country. So it's a really telltale. If you just sat and looked at it for a while, it's a pretty telltale diagram. Anyway, next slide. Can we just put all our telescopes in space? Why bother with ground-based, observatories, right? And most of the data for astronomical and planetary science research comes from ground-based observatories, and whether it be defense, planetary defense, or any topic. I mean, it's just so much easier, so much less expensive, it's so much versatile with instrumentation that you can get to the telescope much more easily. With and with major observatories, they're funded, and they're like an international consortium of effort. And space agencies are operating some smaller telescopes for specific critical kind of data missions, and that's it. And you can't really change anything. It's just what it is, and it's for a specific purpose. So you have like 40 ground-based telescopes that are 3 meters or larger, representing the world's investment of different kinds of ground-based telescopes, and you have one that's bigger than 3 meters, right, out in space, basically. So it's very, very, very expensive to get them up there, and that one telescope is $10 billion over many years of work to get there. So, and ground-based telescopes do critical work, and you all know this. Those of you, how many of you here are amateur astronomers? Oh my goodness. Okay. Well, I'm speaking to the crowd that believes, okay? And you guys have so many things that you do, from comets work to supernova to monitoring variable stars, etc. Exoplanet candidates, even I bet. So it's important work that you do from the ground that you can't necessarily always get achieved as easily with a space-based telescope. And there's a quote here that is from one of our other reports too that stated. So the decrease in efficiency of ground-based observatories due to LEO sets cannot be mitigated by increasing the number of space telescopes. Facilities in space cannot perform the mission of ground-based telescopes due to a wide variety of prohibitive technical challenges. And it's from our from our first report from Doug Point's workshop we had. So going to the next slide. Let's see. So it's a hard problem, and what can we do about it? Following slide. So these are our 4 workshops we had. The first 2 identified issues and formulated recommendations, and the next 2 identified ways to implement those recommendations. And then now, and that was in 2020 and 2021, and I was the lucky person who got to co-chair all 4 of them. And then in 2022, we were incredibly lucky to ask the IAU, we applied with other institutions to be a center to deal with this challenge, and we were granted that. So beginning in 2022, in April, we started implementing recommendations with people from all over the world, and we're still getting organized, to be honest with you. Right now, sitting in your audience is one of the co-leads for the hub for the community engagement. That's John Barentine, and he's made a great job with his cohort in crime, Jessica. And so the kind of things we're hitting first are things like talking to the various satellite operators and trying to get them to do voluntary mitigations, discussing with the US government. A lot of people on the Hill, we've had many briefings, we'll have many more. And we've been talking to other governments primarily through the UN. We presented to the UN a few times. And to make progress towards regulations and funding, that's going to be a long haul, let me tell you guys. And then leveraging, there's a report that comes out every 10 years, and this past 10 years, it's a report by which they prioritize the importance of the proposed astronomy projects. So LSST was at the top, it got funded. So if you're at the bottom, you're not going to get funded, right? So you want to make sure you're noticed. And they noticed us, and they put us in there. They not only noticed the dark sky and the satellite problem, they actually noticed the NOIRLab. They put that in there too. I thought that was pretty darn cool. So, so that was a check there. And then, of course, the software development for all these things I was talking to you about, either predicting the past, or avoiding satellites, or masking satellites, all these things. So next slide. So there are a number of key approaches, and they're listed here. There's only some of them listed here, but that's enough. We want to slow the launches until we better understand the impacts. We're trying to convince them to slow down their launches, but they're money makers. I'm not sure it's going to happen. We want to design satellites with darkening mitigations, and SpaceX has already done a lot of that, but still it's not quite there. We want operators and regulators to consider that there are aggregate or cumulative impacts that will be happening. And we're going to want them to foster, want everyone to foster coordination agreements, internationally and nationally, and we need financial support. We're trying to go for it. And we are looking into applying environmental loss to Earth orbit, which is not, for various reasons, is not being seriously considered at the moment. And then make mitigation of harm to astronomy a requirement of licensing with the FCC and with the ITU, especially the FCC. So that is a big one. And I think somewhere on that previous slide, we might have that as a QR code somewhere we can give you later on. So if you want to look at that summary of what's going on, it's on that one page. Okay, so next slide. Okay. Yeah, okay, good. So SpaceX actually just published their best practices, which is pretty cool. So what they've done to mitigate the situation of the brightness. And that's worth looking online for. It's a very good read, very thorough. In the first generation, which is the ones that are being launched at the moment, they're going to have at least 4,400. I think the originally was 12,000, wasn't it, John? I don't know what happened there, but the next generation is still geared to have 30,000. That's just one company. So over 34,000 satellites from one company the next, at the end of the decade or so. But they are proactively sharing their satellite positions and trajectories, which is kind of a good thing for us. And so we can predict where they are and stuff like that. They are going to be using, and they have been using a bit, one version of sort of like a sticker that has a mirror on it that reflects light in a particular direction. And you'll hear that called like a Bragg mirror or something, we'll call it. And that's what they mean. It's specular. It's only in one direction. And that's the kind of material that they tested it a little bit, but they have a better one supposedly that they'll be putting on the next generation, supposedly. And then trying to darken everything else that's pretty much exposed. Most everything else, not totally everything. Some things it can't because it heats up the element too much. So anyway, and they retired DarkSat, but there's some probably still up there, ViruSat. And they did it for different reasons. DarkSat heated up too much because of the coding. ViruSat was interesting because they wanted intercommunications between satellites. Guess what? They had to take down the visors to do that because they're laser communication. So, anyway, one step forward and two steps back, right? All right, so there you go there. So we do have a new international center, and I'll just mention it here very briefly. It's pretty darn cool. It has 4 parts to it. And I think those 4 parts pretty much sum up the things we have to be working on. And one is called SatHub, and that has a collection and analysis of satellite observations. And they do have a data repository that I think they're only taking FITS files though. But you can actually download if you want some, and you can also upload if you want to. And it's called Trailblazer. And I might gloss over those slides because I think we've been here long enough. But and then there's other software tools we're working on, as I already mentioned, and we're doing some training so people know how to use those tools. And we're doing some outreach to anybody who wants to be part of the community. And the rest are self-explanatory. We have a policy hub that's both international and national. We have a community engagement hub co-led by John that you can ask him more about later. And we have an industry and technology hub with actual industry members and who are the main members of that particular hub to try to do the same thing that SpaceX just did with a best practices guidelines. They have a draft of already. Okay, so that's pretty much SatHub in a nutshell. There's various areas. I don't know if you really have time to go in. I think we want to move forward. So SatHub, if you want to ask me more, and go to the next slide too. And then that's Trailblazer. If you want to ask me more about how you can upload and download and stuff like that, we can go over that one later as well. And what's the next one? So this is just things you can do because I know people ask sometimes, what can I do right now? How could I learn about things? And there are those 4 reports. And if you just kind of Google SatCon1 or SatCon2 or Dark and Quiet Skies 1 and 2, believe it or not, it'll come up. And you'll be able to download those reports pretty easily. And there are some Gonga articles out there. So really great articles like Josh Sokol's article called The Fault in Our Stars. That is worth reading. No kidding. And you can join one of our hubs, and you can do that easily by going to that website. That was very easy, cps.iu.org. At the bottom of the page, you can hit the join, become a member button, and then say which hub you might want to be in. That's why I highlighted SatHub, because I thought you guys would like that best of all. Sorry, Joe. Okay, so
Hi, Scott.
so the future of our sky is on the cusp of changing. Let me just kind of go to my slide here.
Late. Okay, so let me call you back and
well, I'm on the last slide anyways, but I just want to tell you that the story
Hang
is
on,
far
Miss
larger than astronomy versus the satellite companies or the satellite internet, and billions of dollars are being invested and are fueling this industry in all the launches at an exponential rate. And astronomers are having minimal funding, and there's just a handful of folks right now working on all this stuff to try to mitigate the situation. And the regulation is moving even slower. I bet you can believe that. But so I'm just saying now, while you can, go out and enjoy that night sky.
Connie, given the speed that governments move, is the train already left the station and it's never coming back?
It might be the case, but we're going to try as heck to come to at least a compromise on how best to mitigate the situation. Like, we're not going to be able to, we might be able to get some regulations through. Maybe we might be able to tighten the licensing and make them be able to have a couple of things they do to mitigate the brightness, but it's not going to ever be, I think, as strong as we want it to be. And we're trying to for strengthening NEPA laws and things like that.
But they pass a law, or they propose a law, goes to public comment. How many years is that
Yeah,
process
I
gonna take?
know. And then just, that's the truth. That's the truth of it. So the train might have already left the station, but we're going to try still as best we can. Because I think of it as like plastics, right? Plastics we thought was the best thing since sliced bread, and then we just made so much of it and we dumped it, right? And we created a situation we didn't predict we'd ever create. And I don't want that to happen here. But there's a bunch of us that don't want that to happen here. We want to be responsible about launching satellites, want to be responsible about not, having them as bright as they need to be. They think they need to be. There's a lot of things we can do.
I had 2 questions, but I'll let people go for the second one. First is, is this mostly a problem due to active satellites that you anticipate, or is junk a significant part of it too?
Oh, junk's a significant part of it too. Do you want to address that, John?
It's definitely both, and the amount of debris is rising quickly. And you might have heard of this thing called Kessler syndrome, where the debris generation runs away, and every new piece of debris is a potential target to collide with something and make more debris, resulting in not unrealistic possibility, but it's impossible to access the space within even a few years. So we're equally concerned about that. And Connie alluded to it a little bit. She mostly focused on the streaks, but what about all those objects that are too small for the camera to resolve them? So in the same way that all the unresolved stars in the Milky Way adds up to the whirling clouds, this is going to make the sky itself brighter at some level. And the conclusion was we've got to avoid generating a lot of debris to avoid that scenario.
And deorbit as quickly as you can.
Yeah.
And as safe as you can.
So I feel like there you might be lying, like you're impressed in the satellite launchers to some degree.
Actually, I think he had a question next, and then
Sorry.
you, I'm sorry, Richard.
Oh, I have grandchildren, and remember the movie Wall-E? Wall-E,
Yes, yes.
when he leaves Earth, they pass through this debris field, and they actually have an image, and it looks just like that one of the first slides. And it was like, he's getting hammered as he's being yanked, out of Earth orbit. And I thought, yeah, somebody knew what was going to be happening too,
That was pretty prophetic. Yeah.
Is there a plan to deorbit any of these communication satellites, or are they in low
Yeah,
enough where
well-
they'll deorbit themselves eventually?
Well, the higher you get, the longer it takes.
Right.
So right now before now, it was at 550 kilometers altitude, it was 25 years. But recently, and then if you go higher, like 1,000 kilometers, it's 100 years, right? Before any of these things. That's a long time.
That's the
But-
self-deorbit.
But the good thing is, I think it was the FCC just passed something where it's 5 years. Yeah, now it's 5 years for that 550. I don't think it's,
So they have a deorbit thruster on the bridge.
I'm sorry.
Are they gonna have a deorbit thruster, a retro rocket to bring them down?
I think some of them do. I think some of them will come down just sort of naturally. But you're right, if they have to do it in 5 years, they probably have to have a thruster.
This is all US based stuff. What about China and India?
Yeah, that's the next question.
That was my other question.
Yeah, China is being very closed about any conversation at all. We're trying very hard. We have collaborators at the national, observatory there. We're trying to reach, and they reach somebody else who's more in the know. The GW, Guowang, something, is the one that's putting out 13,000, and they may already have some up there now. We just
We're
don't
just
know.
on the-
Good questions.
Thank you.
Everybody, thank you.
All right.
For somebody even better.
Okay, all right, so up next is John Walker, or excuse me, Chris Walker, and
John was my father.
was he really? Okay. And Chris, I don't know very well. This is our first time to meet, but your wife has been telling me about all the amazing work you do, and that you've been doing work in Antarctica quite a bit, 14 excursions to Antarctica.
She keeps count.
Yeah, right. And so, I'll let you introduce yourself a little bit more, but we're happy to have you on.
Thank you.
Thank you very much.
So I'm Chris Walker. I'm the other half. I won't say the better half. I'm the other half. And Connie had one slide on radio astronomy. I have like 40. So I'll make up for her lack of radio astronomy. Also, Connie started out in radio astronomy. In fact, I was her telescope operator for her thesis work at the Caltech 7mm Observatory. So yes, over the years, I've ended up migrating my work to Antarctica for reasons that I'll talk about here in just a second. So I'm gonna go ahead to the next slide. right? I usually start out this way when I give a public talk, you know, sort of the big picture. We live on a planet teeming with life, in a galaxy. How do we get here? Where do we all come from? So where were we all 4.7 billion years ago? Where were you? Answer. So that's right. That's right. So what this picture is actually from site testing on Mount Graham back when Connie and I were grad students. That was an image of the night sky, and there's a clear night, and there's the Milky Way, and all the clouds and dust you see are the interstellar medium. And on the perimeter of the circumference of the circle, you see a couple of bright things. That's Phoenix and Tucson, and then you see trees. So it's a great astrobiology slide. So how do we come to exist in all of this? Next slide. We came from the interstellar medium, from the gas and dust between the stars. That's where we came from. 4.7 billion years ago is about when the sun formed, and from the contraction, gravitational collapse of gas and dust, there's enough stuff in one place that gravity is able to squish it all together. And as it collapsed to form the sun, it spun out a disk, and material actually would accrete onto the newly formed sun through that disk. And once the accretion stopped, the residual accretion disk became the solar system and the planets that we exist on now. And we are actually byproducts of star formation. Planets are the byproducts of star formation. We're byproducts of planet formation. Next slide. Okay, so how do we probe the interstellar medium, the gas and dust between the stars? Well, the dust, it looks black and all that, but for every little bit of dust, for every gram of dust, there's 100 times more gas that we can't see. So how do we probe it? So we probe it by looking at various emission lines and absorption lines from that gas. And the atoms and molecules within those gas clouds act like little radio transmitters, each little one. Any one you can't detect, but when you get 10 to the 55 of them and per cubic centimeter, then you can detect them. And so this is what we do in radio astronomy is we have these very high frequency receivers, which allow us to tune into the gas in the interstellar medium. And the interstellar medium has a life cycle associated with it. And you can it's a cycle, so you can pick up any place and go around. But just imagine you start at the top, this hot, dense gas, like hot hydrogen gas out there. And then over time, it radiates away its heat, it cools down. Gravity is able to start to make it collapse to form first a cold hydrogen cloud, then a cold molecular hydrogen cloud. Then enough stuff gets, enough lumps and clumps in those little clouds to create stars. And then stars evolve and destroy the cloud from which they came. And so all these different stages of the life cycle of ISN can be probed with different atomic and molecular emission lines. And the ones that my group does are the ones circled with little gold. So we look at ionized carbon, ionized nitrogen, oxygen, carbon monoxide. And the brightest of all of the emission lines is ionized carbon. It's the brightest line in all of the universe over all of time, which is a little bit surprising because I think it's hydrogen and helium. But what's the third thing a star makes is carbon through the nuclear fusion process. And when the star goes supernova, the heavy ones, they spew that carbon out. And that's why it's everywhere. And it's also a reason why it's the center of life, the organic chemistry. And also carbon has 4 electrons that can grab on and hold to form complex molecules. And that's why carbon's so essential for the evolution of life. Next slide. All right, this is actually Adam's. Is Adam here yet? It's actually an Adam Block slide. So the bottom slide is a picture of the Horsehead Nebula that Adam took an optical light from, I think it was from the Sky Center of Mount Lemmon. We're all used to seeing that. And then the slide on the top is what my team made, exactly the same region, but in the light of a different thing. That's the light of carbon monoxide molecules. And the gas hides out inside the dust. Every little bit of dust means there's 100 times more gas. And so when you look at that, it's like, well, that's pretty messed up. Look at stuff. In fact, since that's the molecular line, we can look at Doppler shifts and stuff and deduce the velocity fields within the clouds. So that image is velocity coded, the one on top. So blue means blue shift, the stuff's coming at you. And the more reddish stuff means it's going away from you. So you can see that that top cloud is very turbulent, messed up. And that's because there's shocks and star formation and all kinds of stuff happening in there. So optical astronomy gives you one side of the coin of what's going on, and radio astronomy can help probe the other side. Next slide. All right. So these emission lines that we're trying to look at from these ionized carbon and nitrogen and all that stuff, they turn out to be at very high frequencies. So in this plot, it's a plot of atmospheric transmission on the y-axis and frequency on the x-axis. So the very top of it would be 100% transmission, 1, and low at the very bottom is no transmission. And then that's frequency at the bottom in gigahertz. So that's thousands of megahertz. That's where these lines emit. And you can see the atmospheric absorption. So at all but the lowest frequencies down there, a few hundred gigahertz, you can see about 50% of the time through the atmosphere, 50% transmission. But when you get to the very high frequencies, any little bit of water, it's water in your atmosphere, sucks up the light. So water is what is the light pollution for people who do radio astronomy. So what you have to do, just like with optical, is you try to get above as much of that terrible pollution, as you can, or interference. And so you go to mountaintops. And one place you can go is the top of Mount Graham, and that's we have the Heinrich telescope up there, which is a 10-meter radio telescope. And we've built instruments for that and used that a whole bunch of times. But even at the height of Mount Graham or even Mauna Kea, which is what this transmission plot is for, which is 12,000 feet altitude, it's not good enough to do these high frequencies. We have to go somewhere else. Next slide. Well, you can go to Antarctica. That's one place to go. That's the green transmission curve. But even that isn't the greatest. But for ground-based observations, Antarctica is really good. The second one down, the red one there, is from the high Atacama telescopes, where like ALMA is and stuff. And I think, yeah, actually, yes, when I say 12,000 for Mauna Kea, you think that is that 14,000 or 12? 14,000. I spent too much time there. The oxygen didn't. In fact, when we would use a telescope up there, I used the Caltech Sonoma Observatory, we kept a tank of oxygen in the kitchen. So you could go down and take hits of it when you're getting tired. So that's at 14,000 feet, that's right. So the high Atacama one there, the red, is at 16,500 feet. And there's actually a radio telescope up there that I've been to and we've used in the past. But even in those extreme cases, it's still difficult sailing to get these high frequencies. Next slide. Yeah, but anyway, Antarctica turns out to be the best place. And so a lot of people, when you talk about you doing astronomy in Antarctica, they're very interested in how you get there and what it's like. So I have some of those slides. I hope that's okay to show you guys. It's kind of fun. So how do you get there as an astronomer is that we're funded through the National Science Foundation, as is NOIRLab. And so what happens is you take a commercial flight to New Zealand, like it used to be United, then it was American, sometimes it's Delta. You go to Christchurch, New Zealand, and then from there you take military aircraft down to Antarctica. And I'll show you what that's like. Next slide. All right, so you go to Christchurch, New Zealand, you get off the airplane and go out to baggage claim. And if you look down, you'll see there's these yellow boot prints. And that's so the people who come and go to Antarctica know where to go, because within walking distance of the Christchurch airport, there's the Antarctic Center. And it's like a little museum and a cafeteria, but also it has the logistics hub for getting to Antarctica for not just US scientists, but many other scientists who go to Antarctica. And when you go there, they give you all the clothes you need. So Connie can tell you, like the night before I go to Antarctica, it's like I pack a little suitcase. It's like, why don't you bring a lot more stuff? Because what happens is they have a clothing distribution center there where they give you all the parkas and the hats and the gloves and boots and all that stuff, even socks, to go to Antarctica. And then from there, you go down. Next slide. You can go ahead and go to the next one. All right, and so how do you leave to go to Antarctica? You get up very early in the morning. And you go to that Antarctic Center. Next slide. And then you have a briefing, you get suited up, and then you have a briefing, a pre-flight briefing, and then you climb onto the good old C-130 mostly to take the trip down. It's about 8.5 hour trip. This is what the inside of the C-130 looks like if you haven't seen the inside. There's not a lot of comfy, cozy seating. Yeah, you've been there. And so you kind of just tossed in there with all the cargo. And my favorite briefing, you have all these briefings from the pilots. It's an 8.5 hour flight down there. And there's, and these airplanes are kind of old. They're built, a lot of them are old, built in the late 50s and 60s. And the best briefing, and the shortest one, the guy said, well, if there's a problem, there's going to be this light that flashes and you'll hear a horn. He says, just hold on to something tight. You're going to crash and you're going to drown. So just make it happen quickly. And that was in the briefing, and we left. Next slide. But Connie didn't hear that. And if you're really lucky, you get to go down to a C-17, which is a lot faster. It's a 4.5 hour trip instead of an 8.5. Next slide. Right, when you land in Antarctica, this is what it looks like. This is the C-130 coming in, McMurdo. Lands on the ice. These airplanes have both skis and wheels on them. Next slide. Right, and you get off of it, and there's this thing called the Ivan the Terrabus that you get onto. A lot of this stuff down there is built by Canadians. It's Canadian stuff. So they built this big old thing, and you get on it, and you go in, you get all these briefings. You go to McMurdo Station, which was built in 1957, right? That great year. I was born too, by the way. So you get all these briefings. It's kind of like a mining camp, you know, what it kind of looks like with dorm rooms. Next slide. Oh yeah, up in the left, top left, that's Scott's hut. Remember Scott, the British guy who tried to go to the South Pole. He made it. He got back, but died before he got back. That's their hut. And you can actually go in there and still see all their stuff, but it's all been frozen since the turn of the century, the last century. Then there's various places you live down there. It's like a bad dorm room. Next slide. All right, and sometimes, you know, most people stop in McMurdo, and I'll get back to McMurdo in a minute, but sometimes you can go on to the South Pole. And the South Pole, it shows you a little arrow from McMurdo to the South Pole. And you get on another plane. Next slide. And this is what it looks like out of that C-130 flying to the South Pole base. Those are the inter-Antarctic mountains. Next slide. And this is what the South Pole base looked like when I first started going down there in 1995. There's a big geodesic dome to keep the cold out and the warmth in. All that used to be built on the surface, but over the years, the snow accumulated. Next slide. Yeah, we'll keep it going. It's all right. And if you go into the geodesic dome, there's other little buildings inside that you would have like a galley and places to sleep and stuff. Next slide. And this is a wonderful galley that you would have all your meals in. Next slide. And on Sundays, the scientists cooked and washed dishes. And here is the facility I worked at for about almost 10 years. So the South Pole Station is over there in the distance. You see that. There's the C-130 that brings people in and out. And then there's a place called the Dark Sector, about 1 kilometer away from the station, where we would have our telescopes. There's a bunch of different telescope experiments going on there. This is the one I worked on. It's a 1.7 meter off-axis parabolic dish telescope. So the light kind of comes up from like 45 degrees, comes in, hits that, hits a secondary, and then is actually shot down into that mobile home looking thing. And it's on stilts because of snow drifts. And you can't see it in this picture, but just on the other side of that airplane is the actual geographical South Pole. There's a ring of flags, and actually they have a pole sticking out. Next slide. Oh, wait, don't go yet. Sorry. Back up one. So I want to explain what the other things are. Hey, yeah, I know. So remember I mentioned a little while ago, these lines, these atoms, molecules, we're looking at like little radio stations. So there's a graph right there. It says sort of loudness or volume is on the y-axis and frequencies on the x-axis. And just like you tune a radio, you would hear like off there, off of the side, be like static stuff. And then you tune in to a carbon monoxide line, then like a radio station has a specific frequency. Carbon monoxide has a bunch of frequencies actually. You keep tuning, you go to static again, and then you keep tuning, you'll pick up a carbon line. You keep tuning, you get another carbon line. So those are little radio signals. Those are from atoms and molecules from that cloud. This is 6334, which is the Orion of the South. So you have the Orion cloud, everyone looks at, and the Antarctica in the southern hemisphere, you go look at that one. And that map is color coded in CO molecule, and it actually was taken with an instrument we built. And basically what that traces is temperature in the cloud because it's an optically thick line. So where it's the brightest is where it's the hottest. And that's where young stars are being made. Next slide. Okay, this is going down. The light's coming through that hole in the roof. And this is the weird looking instrument that we made. It's just a really high frequency radio. It actually has a few radios in it. And it uses superconducting detectors. So it has to be in a cryostat with a tank of liquid helium. And the instruments are actually bolted to the bottom of the tank and look out various windows. It bounces off mirrors going up to the roof. Next slide. And then we've also gone even further out onto the ice. The South Pole base is at a pressure altitude of about 10,500 feet, about the same as Mount Graham is. You like to even be higher. You say, why is that? Why is it so good then? Because it's not much higher than Mount Graham. It's because it's so damn cold. Because whatever water is there in the sky, most all of it's frozen water. And frozen water doesn't absorb the light that we're trying to detect. That's why. So if you can go someplace even higher in Antarctica than the South Pole Station or anywhere you can go down there, it's going to be so much better. And this is actually on the summit of Dome A in Antarctica, where our team led, this particular experiment was led by Craig Kalesa, who's at the U of A as well. We had a little remote observatory, and you would fly in, they would dump you off with a tent and literally a guide, so you wouldn't die for a week at a time. And then you work on your little experiment, and then you leave it there and hopefully go back to visit it in a year. And that's called heat. And it was also you looking at these molecules out in space. Next slide. All right, let's go ahead and there you go. You got to click it. So what we do is that when we look out through space, we look along different lines of sight through the galaxy, and then we map it, make maps and stuff. And so what we're able to do is look through multiple spiral arms in the galaxy. That's what you're looking at there. Each of those vertical bars of cloudy stuff is looking through one spiral arm in our galaxy, through another one. And this one is showing you what it looks like, those arms look like in different atoms and molecules. So we're actually able to locate those, where those atoms and molecules are along the line of sight because of their Doppler shift and the fact that the galaxy is rotating. So in the end, if you can back out that velocity information because it's spectroscopy, we can make a three-dimensional map of the Milky Way and look at it from all different angles. Next slide. Yeah, you're waiting for you. Okay, and this is the modern, this is the new South Pole Station. This is what it looks like down there now. It's pretty classy. Next slide. All right, but still, even from Dome A in Antarctica, we're at very high altitude with all the cold water frozen out. It still wasn't good enough. So what we need to do is fly balloons and put our payloads on balloons. So ideally, you'd like to go do evil things like put your telescope in space and have it orbit the Earth to go to L1 or L2 and do observations. Like Connie says, that costs a whole lot of money. It's some intermediate ground. So one thing you can do is use high altitude balloons. And this is actually from a How and Why Wonder book. Some of you guys might remember these. I don't know. My mom brought this home from the A&P to me in 1961. I still have it. And I remember looking on the cover, it's like, what is that weird vertical thing there? That's a high altitude balloon. And your payload goes in the bottom. So this is what I ended up doing for most of my career, is doing that thing. Next slide. All right, so where do you go launch these balloons in Antarctica? NASA has a long duration balloon facility called the LDV outside of Murdo. So you take a half track from the Murdo base. It takes about 45 minutes to get there to this facility. And you see there's two hangars over there on the left, and that's where we put these things together. Next slide. Okay, and this is just a picture I took on a random day. This is Mount Erebus, which was erupting a little bit that day. It does that like all the time. Next slide. And here's the two hangars. This was, I think this was 2016. Yeah, 2016. So there's two hangars. There's an experiment with the telescope from the University of California, Berkeley. And then there's our experiment there on the left, we're on the right with our telescope. And our telescope was a 1 meter optical telescope. You'll appreciate that. But we did a terrible thing and made it into a radio telescope. So we ruined a perfectly good mirror by using the radio photons bouncing off of it. Next slide. It's that anticipation. All right, so what happens on launch day is that it's brought out and hanging from a crane, and that's in the middle. But that's a picture of what it looked on the left of what it looked like in the hangar. The whole observatory that we fly from this balloon, it weighs 2 tons, is 25 feet high and 25 feet wide. You can climb it like a jungle gym. It's huge. And in the middle of it is a 1 meter telescope, and right now it's a Cassegrain telescope, and it's just off to the side. And what we're doing at this point is we're practicing the observing. This is an automated computer controlled thing when it's up there. So we're making sure with the hanging from the hook from the crane and the hanger that's doing the right things. And then we launch it on these high altitude balloons. And the picture on the right I took with my cell phone. This is 2016, yeah. So the payload's at the bottom. It's the Stratospheric Terahertz Observatory #2. It's the second time we flew down there. And the parachute you can see there, the little red thing. And then it has this long neck up to the balloon. And there's actually a collar at the end of where that kind of bulbous thing is, the top of the balloon, where it actually holds the helium up there until it gets up a little bit higher. That collar pops off. And then what happens is, as the helium balloon goes up, that particular balloon has 35 million cubic feet of helium gas in it. A million, that's what it was. Once as it goes up, the balloon expands. And once it gets to altitude, it's completely round all the way to the top of that parachute. It's the size of a football field, or even bigger. Next slide. All right, but before it launches, you have to put it together and make it work. And so, so the picture on the left shows you what the telescope looks like. So it's a legit 1 meter optical telescope with guide cameras and stuff just like you guys use. And then it takes us about a month to put it together and make it work down there because it arrives in like 24 wooden crates. Those are students who just taking snoozes while we're working on it. Next slide. And then there's another graph, that's Kay Davis. It was Jenna Klusterman was on sleeping. She's a professor at University of Southern Illinois now. And then the guy on the right, he was sleeping, it's Chris Groffey's professor at ASU now. And there's Kay, she's a postdoc, I think at University of California, Irvine. So this is the instrument we flew. Remember the blue thermos bottle crash that I had South Pole Base? That big white thing is a big thermos bottle as well. And we put liquid helium in it. So I'm just putting liquid helium in it before a launch here. Next slide. That's okay.
Yeah,
I don't get tired of looking at these, don't worry. Yeah, and again, these are superconducting detectors, so we have to use liquid helium to cool them down. And what's behind me there is the, one of the two large solar panels that provide 2 kilowatts of power to the payload. And that's what powers it during flight. And here's a picture of it coming outside on a launch day. Yeah, it's a pretty thing. Next slide. Oh, while it's transitioning, I'll keep talking to it. On the very top, you see that boom with all those like mushroomy things. Those are telecommunication antennas, so we can communicate with iridium satellites and with TDRS while this is in flight. So we continually can get all the data down, and also we can command and control it. And it's just going out to be launched. Next slide. Yeah, here's about half of us out there. The other half are actually inside the hangar doing work. So the balloon is being inflated on the left, 35 million cubic feet. What you saw in the hangar is hanging from that crane on the right. And then when it launches, they release it on the left, and then it floats over until it's vertically above the crane. And then they will it has little pinchers at the top, and let it go, let it fly away. Next slide. Right. Oh, look, it is working. So this is the launch. So they let go of the balloon, it's flying up. And let's see the shadow of it go across. And it has kind of a roaring, rushing sound, is what it sounds like as the helium kind of unfurls the balloon. You can see the parachute straight in. So what's the deal with the parachute? Well, what happens is that there goes the shadow pass. At the end of the mission, there's explosive bolts on the top of the parachute, and it separates from the balloon, and it all comes back down again, so you can fly it again. Just like an Estes rocket. Who had Estes rockets? All of us, right? It's like just an Estes rocket.
I'm doing a model rocket program at the school. I started in 2017. I could not believe Estes was still in business.
Really? It's awesome. Yeah, my dad, the first time we took it out, he said, "You have to connect it to the car battery." And he was all mad, but then he sat in the car until it went off. And then I didn't have any trouble ever having to take me out to fly. And there it goes flying off. And it goes off around Antarctica. Next slide. So what happens is it goes up, and then it gets caught in the jet stream. It's called the anticyclone around Antarctica. And it takes about 2 weeks for it to circumnavigate Antarctica. It will almost come over the exact place you launched it. And at that point, NASA will command it to the explosive bolts to go, and the thing will parachute down and recover it. This is the control center we've had at the lab in Alberta. So the things on the left are used to control the gondola, and on the right, we're controlling the instrument. Next slide.
How does the scope stay stationary when it's being blown around up there?
Oh, it's not. It goes around with the balloon.
I mean stationary when you're doing an observation.
It's actually very, very stable. So what happens is that I know this is kind of a side topic for you guys, didn't want to bore you too much. But when you look on the gondola picture back, there's actually 2 reaction wheels. There's a 75-pound flywheel on top. Because you say, well, I can see how you're going to do the elevation, right? It's just a motor. But how do you steer it in azimuth? Well, we have a big flywheel on the top that we spin around. We can make it turn, and we can spin in both directions. That's how we control the azimuth. But then there's sometimes this pendulation. And so we actually have a bicycle wheel that's mounted at right angles to the other reaction wheel that we spin around and to take it out. And then to know where we're pointed, we have 3 fiber optics gyroscopes from Russia that we use because they were cheap. You can basically drop them and they still work. And I saw a guy drop one 12 feet from the top of the gondola all the way to the ground. It's like, but it still worked. It still worked. So we have fiber optics gyroscopes. We have the reaction wheels. We can actually, on a good night or good time, we can get a half arc second pointing with it. And here's a picture of the data that comes back. So on the right is those little like spectra. that we take, like scanning a radio receiver. This is an atomic carbon. This is made with our instrument in flight, and we're looking toward Eta Carina, which is a really messed up place because it's two massive stars orbiting each other. One is about 50 solar masses. Another one's like 140 or 50 solar masses, which it's like you shouldn't exist. You should go supernova. And the larger one is thinking about going supernova, it's erupting and stuff. And it comes from a very churned up region. So that's an optical picture on the top left. And there's another optical picture on the bottom, negative. Then we're looking at that region of atomic carbon, ionized carbon. So it worked. Next slide. Yeah, we actually got more spectra, and the reason I'm showing you this is that we got 1,000 spectra, 1,100 lines of sight toward Eta Carina, which is 1 square degree in about an hour, and that's more data than the Herschel Space Observatory got toward this region in 4 years. And when I showed this plot at NASA headquarters, they gave us a $50 million grant to build the next balloon-borne payload after STO. And we're actually going to launch that next year from Antarctica. Next slide. And this is just another map of Eta Carina. You can go ahead, it's a movie, so maybe click it. I don't know whether it's going to run or not. If it doesn't, we can just go to the next slide. Okay, no problem. Let's go to the next slide. Because I have the next slide. I showed a still picture.
Is that the next slide?
Yeah, that's the next one.
Okay, it didn't run.
Okay, it's no problem. So Eta Carina is down on the left where I have the circle around that blue thingy. That's Eta Carina. And then it's sending shock waves up, and all the modeled stuff up. It's a giant molecular cloud, and the UV light from Eta Carina is creating shock waves and actually lighting up the molecules within that cloud. That's what the more topographical things are. Those are the maps we made with our observatory. Next slide. We had a big AppJ paper about it. And so the bottom left shows the flight path that the payload took. It actually went around Antarctica twice, sort of spiraling in. And we ran out of helium about the end of the second orbit around Antarctica, and it parachuted down. And just about that time, there was a traverse team bringing a train of sleds of supplies and refuse back from the South Pole Station. And they were able to go with it. We actually were able to drop it within 100 meters of them. And they picked it up and brought it back. So what you're seeing in the middle there is actually a picture of the payload after it was recovered, after flight. Solar panels were all banged up, but otherwise it was in perfect shape so you could fly it again. Next slide. I think we're nearing the end. Right. So yeah, okay, might as well. So this is a picture of what it looks like inside. This is at McMurdo. I showed you the old galley, the South Pole base. This is the galley at McMurdo base. It's a Sunday night science lecture. I've given a few of those there. And it's, most everybody comes to the science lecture. The base has about 1,100 people, and most of them show up. That's how boring it is. I mean, in Antarctica, it's so great. You go there to McMurdo in particular, you're there for after about 5 days, those C-130s start looking good again. Yeah. So people look for stuff to do. All right, then, yeah, next slide. And this is a picture. I took these pictures. This is Thanksgiving dinner. I missed with Connie 1 year, but they tried. I missed many Thanksgiving because I usually go. I'm usually there for the Halloween party, and I come back, after New Year's when I go on these campaigns. So that's our crew. They're a very good-looking group. I'm not in the picture, thankfully. I took the picture. But yeah, it's a big deal. They try to make the holidays special down there so people can sort of ground themselves in reality so they don't drift. Next slide. And they even have a rock concert They have little races and all kinds of fun stuff at these different locations. I think I'll stop there. I've talked too much. I just want to kind of give you a flavor of, oh, well, there's the bar picture. Okay, you caught me. There's actually 3 bars in the Ordo, and they're always full, and a coffee house. All right, thank you very much.
Any questions?
This was the fun talk. Connie gave the hard. This was the fun talk. Thank you very much.
Right, thank you very much. Thank you. Love to have you give talks in the future. So we can take just a few minutes break as we transition to Steve Edberg. He's a retired JPL planetary scientist, retired professional astronomer. He was on the Cassini mission and many others. And so stretch your legs for a few minutes and come back. And he's zooming. He's coming in by Zoom from California. Yeah.
So you go to the whole process. It's just, no. I had a question for you. Just on the well, I mean, I got a little face. We'll get it. Well, there'll be people up this. Yeah, we talk about. So you got some stuff. Yeah. Oh, yeah. Yeah. Everything. And how do I get in every night? The gate. Oh, yeah. So the exit gate, we want to start some. Another layer of yeah. I've heard some very really? So you did this very. Guys. She was there we early 2000. Yeah, so for every spacecraft. Yeah, I'm sure. Satellite. Up next to military assets. You know, are you something nefarious? So as soon as we come up with a solution, it's like somebody might use that for. It's I just like that. It works. You mean oh yeah, we'll come to high precision. Oh yeah. I'm not sure. Yeah, I'm not sure. Well, what?
Even now, we're gonna fill in space.
That's pretty fun. Yeah.
Nobody back there. Just people with plastic. What challenge?
Oh, yeah, you read the outer space. It's like most actually first from America to the circuit. That's what they're preoccupied with. So it's so.
Next year.
That is laughable. It is impossible for it to be laughable.
We didn't see the first.
That's fine. That's fine.
Yeah, that's the reason why I do is just. We did SEO on one.
We want to
Yes, someday, but not so much. Healing is always. NASA provides spring loading valve. And then what happened was that hard waves so long.
Classic. I also think it's a form of.
So you're all the way up.
Three G's over. And it's just. And it's almost.
Not the time for everything. One mission to go. Here's our healing. So we got someday.
We were told that even if there was. This is all the best we might hope for.
Next
Outside.
We're already spent almost all the lunch. And then, the first mission it was. All the hard stuff.
It's not so much.
Well, so you're.
And that little activities in space.
Can't, they get fully, mags, and we got it.
Right, like, and then, the Russian defense minister said a few days ago, apparently, that he thinks that Starlink satellites are a good military target because they were providing a lot of data access.
Oh, yeah. I was concerned talking about Starlink. Yeah, we were talking about Starlink. That, it's becoming.
I just don't think the world is trying to get it played out. I don't think the world understands how critical the problem is. And it won't understand that until there's a catastrophe. I honestly thought, I feel like in the next 5 years, there's going to be a massive life accident. And is it too late?
So I think this time.
I always point to it, so it was like Montreal, phased out. That worked. That was a trial. you can't rest on the laurels once you get something like that. It takes policing, but we effectively reverse. The ozone from a form of environmental degradation, but it took the entire world into it. And they had to see that there was pure and present. And until and unless you get to that point, you have no choice. But we can't still, can't make the world to agree that there's a pure and present.
Well, yeah.
Right? The ozone hole came about on this time scale of decades. Right? This is a
Fix their.
yeah, 1 year for the rest of the century is going to be like.
Yeah.
What can we do other than we're out there we're trying to raise awareness of this insanity? It's that critical. You don't care about astronomy, fine. You don't care about telecommunications, fine. You might care about messing around with the upper atmosphere of the Earth, for example. You know, or there's a lot of negative stuff that goes along with launches. A lot of black carbon reaction, carbon circulation, stuff like that. It's the whole life cycle. So, but at the same time, we just do not have the upper hand. So we can't walk in the door and say, "Oh, we're trying to shut this whole thing down." You know, it's going to happen at some level. It's going to happen. We're simply at this point, the best we can do is avoid the worst possible.
Well,
it's fine. It's fine. We're not arguing. And the Outer Space Treaty says the use of space is for everyone, right? Everybody has equal access to this for all of its purposes. That's fine. But we're trying to get back and say, if we don't change the path we're on, no one is going to have access to space. And that's not what we do. Right. Now we just have to do this first of all. Point yes, about that. I mean, as with anything, Montreal, everybody, not just. You had to make sure that by phasing it out of the west, the production wasn't. It's the same thing. There are a handful of methods that are not parts of the outer space treaty. Right now, if everybody wanted to move their launches, so we're using to North Korea, they want
Nobody.
The
Saturday was overflow.
to sort of go.
So,
go
I don't know
find
if tomorrow, just in case I have to go on Saturday, or something to hear. But there's no, not everybody. So are you going tomorrow? Did you register?
You know,
Okay, so.
all we gotta do is.
We're limited to 12
Keep this running. How many people?
by 6.
And we're still.
Well, I was the one.
Yeah, I mean. Be honest, I'm not particularly out.
But as I tell you, if we do nothing, we don't do. The only chance we have is to do something.
I mean, you're saying we're. I'm saying software is. Yeah.
Our website, SATHA do very definitely use yes, and they are kind of doing the projects. And
Yeah. I'm software.
are donating what you're trying to build it. And the management of the center is silent. And we're not very well resourced. We have nothing comparable to a budget. One is so, and we're having to work on it. All that. So we're trying to encourage you. We're trying to still share that we make the other side.
You know, doing other things or whatever. I'll just say that's not my trick. You know?
It's not for everybody.
Yeah.
But there are other things that you do.
That's all we're going at.
Yeah, true.
Yeah.
Truly. She had the website that they were asking for. Yeah, CPS. CPS, or
I know.
Some say doctor.
I always suspect all of them.
The upload system. Yeah. Here, I'm mostly worried about operating servers.
Oh, yeah.
Okay. From the whole repo and then we'll copy the repo. Probably that's the end of it.
Yeah.
So. Yeah.
There we go. I don't think we do it. I just trying to keep your head.
Now, here, here. Y'all should. I was thinking it's a match. Order. What's a good?
Okay, yeah.
It's not so much even about skyfall, that's. So,
We have everybody in that Mike, I think we're going to get started now. Steve has been waiting very patiently here. Thank you so much, Ron. Thank you very much. We will do this. Yep. Wonderful. Thank you. Thanks, John. Okay.
Well, this is like the first sport chat.
Well, hello, everybody. This is Scott Roberts from Explore Scientific and the Explore Alliance. And people are still coming back in, but we're very pleased to start our final segment today of our talks. This time we have Steve Edberg. Steve Edberg is a professional astronomer. He is a retired JPL planetary scientist. He was on missions to Jupiter and Saturn, many other missions as well. And we're real pleased to have him. Whenever I have a question about the solar system or the universe in general, I often call Steve up to ask him questions about it, and he usually has the right answer. Steve also is an amateur astronomer and was with the Riverside Telescope Makers Conference for, I think, over 2 decades, something like that. And before that, he put together one of the early professional / amateur pro-am projects called the International Halley Watch. And that's how I got to know Steve back in the 1980s. Anyhow, Steve, thank you for coming on to the Arizona Dark Sky Star Party. We wish you were here, but yesterday we had a huge rainstorm. You might have been washed out completely. But luckily, late into the night, I woke up about 2 a.m. and saw clear skies. So we're still getting some great viewing in if you happen to be up that late, and we'll see what happens tonight. And it was dark. It was. I took Steve. I took an SQM meter reading at 21.49. So that was pretty dark. So. Yep. So anyhow, let's do a sound check, Steve, to make sure you're muted.
I have unmuted myself. Can you hear me?
Yes. So I'm going to give you the stage, Steve. Thank you so much for coming on.
Okay. Well, greetings, everyone. I wish I could join you, but didn't work out this time. You know, it's a good meeting when the schedule can't be held, and I'm sure Scott will be unhappy, but I'm very likely to overrun my time too, but I'll do my best. I'm going to help you with, I hope, with ideas of what you might do with the other half of the day that's not dark. And actually, professionally, that's where I started my career. I started in solar physics and even have a publication or 2 in that. And then moved to JPL, got into planetary science and even into some stellar astronomy as well, and have now retired and am enjoying it very much and getting back to a lot of basic things. So one of them is observing the sun. So what I want to do today is get you started, if you don't know how, and to safely observe the sun. And if you do, maybe I've got a few tips here that might improve what you can do with it by pretty simple tricks, actually. So with that, I'm going to share my screen, if I can manage it. And that, I think, is what I want. And I'm going to go full screen with my slides, I hope. There we go. So, getting the most from your solar observing and even getting started on it. I want to talk about how to observe the sun, when to observe it, what to observe on it, and actually the observing part too. I hope you'll get a chance to do that, see some of the instruments maybe on site there. And in any case, there's a lot to be said about the sun. It really is the key to a lot of our understanding of not just stellar physics, but even planets, as I'll mention briefly in a minute or so, and to the way plasmas work, which is what makes up a large fraction of the universe. Plasmas being gas-like collections of particles that actually have an electric charge. I mean, overall, they're not electrically charged, but they have separated positive and negative, in this case, positive charged ions and negative electrons that make it. And the sun is basically a huge ball of plasma with a core, a radiative zone where energy travels out just purely as photons, everything from gamma rays to, well, just about everything in the spectrum. into the radio, presumably, though be pretty hard to measure those because they can't get out of that. Then there's a convection zone, which we see examples of when we look, those granules that I will show you in a little while on the left side, and maybe you can see my pointer, are evidence of that. The chromosphere has a separate set of its own super granules that you can see there. And as you will note, there are a number of other things outside. The black lines here are just trying to indicate that there are waves, pressure and gravity waves that we can actually measure relatively easily in the sun. And in fact, they have been even used to study planets like Jupiter. The gas giants are going to have similar pressure waves and gravity waves inside, and spectroscopically we can measure those and learn what the interior of the sun or stars, and we can see them in stars and planets, are actually like. So when I say the sun is a key to our understanding of the universe, I'm not exaggerating. What we can actually directly see is the photosphere. That's the bright white layer that would certainly damage your eyes if you were to stare at it for any length of time at all. The chromosphere that is above it, and I'm going to show you how we can actually detect that in a way that you may not have seen before. We can sometimes see things that are called filaments when they're across the disk. They're on or above the chromosphere, really above. Or when we see them against the sky, we call them prominences. And I'll show you examples of that. And finally, I'm not going to spend much time, but the corona is the outermost layer. That's what everybody gets excited about for seeing at a total solar eclipse. And for anybody who is unaware, there is a total solar eclipse just a year and a half away now in April of 2024, and it crosses from Texas to Maine. So I will close out pretty much talking about that, but not spending much time on it. So let's carry on, and let me talk about those layers. You see, in fact, I've grabbed a pair of eclipse pictures to show that. The chromosphere is that middle layer. The photosphere is the lowest of the layers that we can see closest to the core of the sun. About, you'll see a lot of numbers, but I'm going to say 10,000 miles above the photosphere, we can see the chromosphere. It's that pink layer and mostly hydrogen gas. There are that's because it's much thinner than the gases in the photosphere, and there's a distinct sharp edge, at least visually, that we can see in the behavior of the gases that are in, and really plasmas, I should say, that are there, lead to it having one type of spectrum, which I'll show you, versus the chromosphere, which has a different type. And then in places here, you can see the chromosphere and photosphere are covered up, but there are still prominences prominently above the limb of both the sun and the moon. Little on the one side over here, you see just a little bit short exposure. You only see a little bit of the corona. Longer exposure shows you something like this. And that's what everybody gets excited about. I certainly do. I've been chasing eclipses I was just thinking about it. I couldn't talk my cousin, who was old enough to drive when I was 10 and a half, to take us from Chicago up into Canada to see the total eclipse in 1963. So that was my first attempt to get to a total eclipse. Solar projection, and you can barely see it, little hard to expose with the black of this telescope and the white of the screen, but there is an image of the sun projected through the diagonal mirror and through an eyepiece to project an image of the sun on a screen. Safest way you can go. You're not looking directly at the sun, you're looking at an image that is on a white plate, and though sometimes it might work better to use gray, actually, so you're not as dazzled by the white. And you can't do any damage to your eyes this way. The trouble is, especially if you try this with binoculars, and people do, I have done it with half a binocular, a monocular, but I also used one that was made in the good old days when we didn't make a lot of plastic parts that went into optical devices. And the trouble is those plastic parts can melt in the presence of a solar image going in the wrong place, and you could damage any plastic parts in a telescope or binoculars or single monocular if you were to use this method. I'm not saying it's not good, just be careful with it if you do that. If you want to look carefully, you can see some of the mistakes I've made, and only damaging what you see damaged, not myself, and others that I've been too scared to actually try. Up here, this is I believe it's a Barlow lens with a solar filter in it, sold by a company now decades ago. I don't think they're in business anymore, not because they were selling these things, but I've never had even the courage to try it. This is a Herschel wedge. It's actually a wedge prism that lets most of the light go on through. You can see it actually, this is the solar image coming straight out of the bottom of the telescope, and only 4% being reflected into the eyepiece that's in the far end of the diagonal assembly there. But you definitely would need to have some additional filtering to do that. 4% is still a huge amount of sunlight to put into your sky, especially if you collected it with a telescope. And so you would never want to do that. And that's what the problem with these are. When I got my 60mm telescope, it had one of these. I even used it looking at the sun. I know much better now and knew better long ago, in fact. These can have a tendency to crack when exposed to too much heat. The same thing happened with a temporary diagonal mirror I made with it for my 10-inch Newtonian out of a piece of plate glass, which was flat enough. It's not float glass, it's plate glass for temporary use. And it just got too hot anyway and just cracked just like that. Some people suggest using carbon, which you could get from a candle flame. And I did that for this, not to use, but as a demonstration to just show you how flimsy and easily rubbed off that carbon is. You don't want to do that. At the same time that I was trying to use this diagonal, and before it cracked, I put in a filter because I knew I needed to have that. I was only getting 4% of the light in, and you can see what happened to the filter over time. And again, that was taken out, and I made other arrangements to make sure that I could safely observe the sun with that telescope. One of the things that you want to know about solar filters is their transmissions and what's safe. The idea for safety is that the transmission here and density be high. So a high number is good. The range 5 to 6 is what you typically find. Some of them do go to higher densities, others don't. But you also don't want to get a lot of power or transmission necessarily in below certainly 5, a density, optical density of 5, which means it's passing 1/100,000th of the light that's falling on it. You can see that plus X negative film here is passing in the near infrared and deeper into the infrared. What would still be, you're risking damage to your retina by looking through this material. You would never use color negative film. It's pretty hard to find film nowadays. Black polymer like this is common, and this is not good at this end, but it is still marketed and used. That I'm partial to glass, which has, and I'll show you some of those, has metal evaporated on it. Water solar film is very good. Solar screen is good. My personal gripe with it is aesthetic only. It shows a bluish image. And then there's welder's glass, number 14, safe and marketed, but I'll in a minute tell you why you probably don't want to use it. So here are some of those samples, in fact. Welder's glass provides this green material. It is glass. It does a good job of, fairly good job of absorbing the infrared. And it's safe for welders. It's basically safe for the sun. But the surprise I got was when I was trying to actually take this picture, and you can't really tell it here, but actually it's focused pretty nicely at the north and south limbs of the sun. I should have said that north and south, but it doesn't really matter. East and west is out of focus. And who'd have thought that you could have a material like that in a flat piece of glass, but that's what it's doing. It's actually producing defocusing that just does not provide good images. This is polymer on screening material, and it gives you, this was sold as solar screen, and gives that bluish image. I personally don't like it, but it's purely the aesthetics. It's safe. I am very partial to metal on glass filters, and I will tell you, yes, off-axis and sub-aperture filters are relatively inexpensive, but if you can possibly do it, it's worth getting a full aperture filter because of the resolution you get. You'll typically find an orangish or even a whitish color to that, and you can usually freeze the seeing that we have, usually worse, I would say, during the day, but not always, by taking short exposures, even with a lower density if you need to, but oftentimes you can get away with that, jacking up the ISO. And full aperture is good because there is resolution to be seen. My experience was one day I was using an off-axis filter, not on this 5-inch comet catcher, but rather on a C8. And well, it looked like a good image of the sun. And then I thought, okay, I'm going to pull on my full aperture filter and see what I can see. And the difference was amazing. I could not see the solar granulation, which is about 1 arc second on the disk of the sun, with that off-axis filter, even one that was bigger than you're seeing here. But I could with the full aperture 8-inch filter on the C8. So I will just emphasize again, the action is oftentimes in the fine detail, and that fine detail requires the full aperture that you have. That's the beauty of being able to use what you might think of as only a nighttime telescope and adding that solar filter, and you get to see a lot more and use that telescope as much as you want. Just to mention metal on glass filter maintenance, but it's true for any solar filters you have. If you see pinholes in them, you want to cover them up. I actually use black paint, and you would not notice any of this. Looks terrible on the filter, which is reflecting more than 100,000. Well, more than, how shall I say, 999,999 parts per million of the sunlight falling on it. But you don't notice all those blobs there. It's just reducing more of the light, and you're not getting any kind of glare through to ruin your viewing, and potentially, though doubtful, you're hurting your eyes by getting through there. If you have too much scratching on a filter and too much light, you do need to discard it. But I just had a lot of pinholes, and I took care of them that way. Comfortable observing, really think about getting a rubber eye cup on the end of your eyepiece or eyepieces for this purpose. It just helps reduce the light coming in sideways when you're daylight observing. You can also pull a blanket over your head to try and reduce that. It works and may make it comfortable, but also oftentimes you're in the sun, it's hot. So you may want to shade yourself under a pop-up, and you may also, with or without using the an eye cup, get yourself a sunshade. I show a mechanical one here, but I have since moved on to getting a sheet of the soft styrofoam even 1/2 inch diameter, the kind that they used to make for sleeping pads, cut them down to something about the size of well, a little larger than the size of the full aperture of the telescope, and you can just slide them over the front end of the telescope and rotate it, because you give it a tight fit, but it stays put, and you rotate it to where it's shading where you're putting the eyepiece in your head, and it really keeps the sun off. Very useful to use. So I highly recommend those. When should you be observing? Well, you check your regional weather forecasts, and you can also use the clear sky clock at cleardarksky.com for your area to find at least when it's going to be clear. My experience, especially at night with the clear sky clock, is that it sometimes doesn't pick up some of the weather that we get in Southern California, which goes by the acronym down in the middle of the paragraph, and that stands for late night and early morning low clouds and fog along the coast. And you can add moving inland overnight sometimes. That may be the longest acronym in history, I'm not sure. But that's one of the things that the clear sky clock does not actually forecast well for my area. Other things where the jet stream is, you can find where high pressure systems are visible. And if you got jet stream and high pressure, you likely have poor seeing. If you have upper level humidity, at least in Southern California, you oftentimes have arcsecond and subarcsecond seeing, and that applies day and night. And when it's like that, it's wonderful. I just had some recently and watched Io's shadow and then Io itself moving across Jupiter's disk. When to observe? Well, it's sometimes not as obvious as you might think. If you're a nighttime observer, you want to get this object near the meridian. The seeing is usually most reduced there because you're looking through the least amount of air. But that's not necessarily applicable to the sun at local noon. And that's because overnight, everything is cooled down, so there's much less differential between temperatures on the ground and in the air, so there isn't any rising warm air. And so a lot of solar observing is done just after dawn. And it got real tough when I was working at Kitt Peak because it was up at 4 a.m. to work on the big telescope, the big McMath telescope up there, to get good seeing at the time. So it's something you want to just pay attention to and learn what happens. Oftentimes it can get settled again late afternoon too. So don't wash out on that just because it may not seem to be. It's something where you have to learn what's best around your area. Seeing, I've already described to you a little bit. It's caused by Earth's atmosphere and waves in the Earth's atmosphere. Looking over as day or night, a hot roof is not a good idea. Looking over a large lake, day or night could be, especially during the day. Solar observatories are built on lakes, either right at the shoreline or even on a causeway out, such as at Big Bear and in India. And they get better seeing there as well because of this. The water settles down the air. Just the same, and I hope you can see it on this, there are patches of good seeing in this picture. This was taken, I think, by one of the telescopes at the Canary Islands. And you might notice that, for example, you can see this is called granulation. You'll see that there are bright cores in it. That's where there is rising hot gas. It flows to the center and flows out cooler, making the edges. It's often called a rice grain pattern, but notice that it kind of washes out in places as well. All through here, it's just not as good. That's seeing just across the disk of the sun. And I'll just call your attention to this sunspot. You see the umbra where the dark places are. Here's a light bridge in a couple of places, and the penumbra here. There's a lot of interesting astrophysics going on here, and I'll get to that in a little while. So where should you observe? I mentioned this already, so I won't spend a lot of time. Minimize the seeing. Lakes and meadows can be stabilizing. Buildings, parking lots, and roofs are not. And you do want to be aware of the telescope's internal seeing. When I am expecting to do observing with the telescope, I will actually even turn on the clock drive, get it aimed towards the sun, even with the covers on, so that I don't differentially heat the tube on one side and cause convection inside the tube that will produce internal seeing. Then I'll pull the cover off, put on the filter, and away I go. There's also something we deal with called differential refraction. And here are a couple of examples of it. Here you can see a little bit of, on the red bottom of the disk, a piece of the sun being torn off. Of course, that's really not being torn off. It's simply that there's a layer of Earth's atmosphere that has a very different amount of refraction than the upper layer. Here you can see a little bit of green flash separated out as the sun was setting over, I think this was the Pacific Ocean from Maui that I got this picture. And besides the clouds there, you see a little bit of a green flash. And so we get that, and that's differential refraction. The reason I want you to pay attention to that is because seeing can be reduced if you pick a very narrow field of view. On the top left, I'm just showing a 540 nanometer continuum filter. It would just be showing you sunspots and the rice grain pattern, the granulation on the disk. But you would not be mixing all the colors of the sun that come out through there and softening the image. You could, for example, if you wanted to reduce some of that, pick one of the filters of blue, green, or red for trying to reduce that. The blue has the advantage, or even into the ultraviolet, though many of us can't see that well into the UV. I certainly don't have my UV sensitivity that I used to. That's part of aging. But it does bring out some of the more subtle visible areas on the disk. Green or red would also do the same thing, with at least settling you into one wavelength range. If you can, though, going to that narrow band filter could be done even with a nebular filter, or by whatever you use, a light pollution reduction filter, whatever your choice of name for it is. They have very narrow zones of transmission. Here, this is in the blue-green, and here we've got red and deeper in the red. But you could, for instance, with our red vision petering out by about 700 nanometers, you could actually get a red filter or an orange filter that would just give you, combined with the nebular filter, this part of the spectrum, and you'd have less seeing effect because you're looking at the red end of the spectrum. The reason I don't say do the same here is because if you got a green filter, it would still, whoops, I got to go back. Sorry about that. Oh boy, hit the wrong button. So I'm going to just step through. There we go. The reason I don't suggest using this part of the spectrum is because most of the filters that you might use for it are going to be transmitting not just from the blue or green wherever you had it start, but would go all the way across, so you wouldn't be getting as much advantage. But getting a filter like this doesn't have to be at 540, it just needs to be narrow like that, will work. And of course, I'll talk about the one narrowband filter narrower than this at 656. That would be right in here, which we use on the sun directly. So what happens with the granulation? I mentioned that we see these things. They're only 600-700 miles across, though it's kind of hard to tell that when you look at the pictures. They seem to be pretty random in their sizes. And the cores have the upwelling gas, which you could see if you watched what happens if you ever make have oatmeal in a pot. It will usually be rising in the center and cooling off and flowing down, that convection at the edges of the pot. Sunspots have very strong magnetic fields. He talks about Tesla here. I'll talk about Gauss. The magnetic field of Earth is about half a Gauss that drives our compass needles. The typical magnetic field of a sunspot in its core is about 4,000 Gauss, and it can get higher. So that gives you some idea of just how strong those magnetic fields are. They seem to inhibit convection, but even so, you can still see granulation, certainly in the penumbra here, this outer lighter part, but also if you were to expose properly, you could see convection still going on in the core. So we're not entirely sure what's going on. If you watch one of these sunspots near the, well, approach the limb, or after it has just turned around onto our side of the sun, our hemisphere, facing hemisphere, you can actually see that sunspots do seem to be depressed. They are lower in the skies, in the photosphere, than the rest of the photosphere. They also have faculae, and this is what gets improved if you use a deep blue filter. You can see this more easily, and it's the brighter areas. Now, I will diverge for just a moment, not any measurement that you can easily make, but you must think, most people think, and sensibly enough, that if there are sunspots, the sun is putting out less energy when there are lots of sunspots. And we're going into a period when there more and more sunspots are rising for the next year and a half, maybe 2 years. That's not actually the case. We actually measure more radiation coming from the sun when there are lots of sunspots because it's coming out from the faculae. Just one of those surprises that is still, we'd like to have a better explanation for. You can watch the sun rotate, and if you have a long-lived sunspot or sunspot group, as we do here, you can not only see it moving across the disk, but you can see it change as it does. And so here you see two groups, a bigger one over here, smaller one down below. Notice as they come around, especially this one has just plain disappeared. This one has grown and gotten far more complex, and then it's losing the complexity as it goes around. It may or may not come back around after the 15 days or so that it takes to make one rotation. Same thing's going on here. Things are going. Notice also that the spots seem to be limited. They don't go all the way to the north or south poles. They are limited to, if you can call it that, the temperate zone on the sun. And here are just some other examples of sunspots. I'm not going to spend a lot of time on this, but will stop briefly here and mention really big spots. This is a spot that is big enough you would have been able to look through a filter without binoculars, but with the filter unaided, you would be able to see that spot on the sun's disk. And it seems like once or so every sunspot cycle, we get a spot like that. And with spots like that, it's been my observation that you're likely to find that there are going to be some huge solar flares in the area of spots like that, because the magnetic field gets so complex that the sun releases some of that energy in a solar flare. I will get to that in a minute or so. As I said, there is a sunspot cycle. At maximum, there are going to be many sunspot groups on the disk. They will be constantly changing, and you'll be able to watch the sun's rotation every day by just seeing how much they move. Sunspot minimum It gets really boring, I will tell you, on the disk. Though I will point out here, you can see a little bit of faculae here and faculae here, even just near the limb of the disk. But we went for a couple of 100 days at one recent solar minimum with no sunspots at all. And you can get, there are numerous places where you can get a look at the disk from telescopes, either in space or on the ground, with just essentially an integrated light view that shows what the disk looks like, matching something like this. Sunspots appear and disappear over time. This is the period from 1880 to 2010. And you can see two things with these charts. One is that the sunspot area varies over time. It has peaks over time. The 1958 or so was the peak in terms of sunspot numbers for forever, as long as we have records, which now go back to about the 1600s directly with sunspot counts. And you'll notice that it was a big peak at that time. It did come down, and it's been down ever since. There has been some speculation then we get out here into the 2020s that we may not get many sunspots at all or none. I think well, it's not good to make a prediction like this, but I think we will certainly see some sunspots with this coming peak, but the game is to figure out how many they're going to be. What you can also see with this, which is called a butterfly diagram, is that at the beginning, and I'll just start it with the 1880 one just because it's clean, you see first sunspots appearing at high latitudes, and over the years, they get closer and closer to the equator. And that is something that you do see throughout this period, and is common. We just have come to expect that, but that very few sunspots at the high latitudes are ever seen. So you'll be able to watch that over the next couple of years now as well. One other thing, you might think, okay, if we have the most sunspots peaking actually typically 3 years after the beginning of after the minimum of the cycle, 3 to 4, and then it tails out for the next 7. The average is 11 years, but it ranges from peak to being 7 to 14 years. You might think that the solar flares are going to be at the maximum sunspots. Answer is no. It's usually a year or two after maximum sunspot number. So that's a way of telling you also don't give up on seeing interesting things going on in the sun after a sunspot maximum. Are there any ties to the sunspot cycle? Well, this is to suggest here that the number of Republicans in the US Senate follows the sunspot cycle. I don't buy it, but I don't buy that there's a connection. It does seem to have happened, but we might want to go back prior to 1965 and actually do a much longer period than this, but this is a cute thing. There basically is no tie-in that anybody is aware of with Earth's weather or climate with the sunspot cycle. And we do see changes in cosmic rays, which we can track through looking at tree rings. And we can also see, of course, weather changes with those tree rings as well. So there's paleoclimatology addresses some of that. Now I'm going to talk a little more about the spectrum. This is not the best picture. I don't know kind of what really happened to it, but you see a number of different spectral lines. This A line over here is actually deep at about 0.7, 700 nanometers, I'll say, easiest way to say it. And that's actually a gray area where there's a lot of oxygen in Earth's atmosphere absorbing sunlight. The C line is hydrogen alpha, H alpha, at 656.3 nanometers. I grew up, it was called 6563 angstroms, and we do a lot of science here in that spectral line. The D lines are from sodium. They're also used somewhat with one of them being the one called D3 is actually a helium line that we study a lot as well. Over in this area, there are lines that we use for studying the sun's magnetic field, and very commonly you will hear about the K line and sometimes the H line of calcium mentioned up here. This is the angstrom symbol, 396.8 nanometers, 393.4 for K line nanometers as well. So that's the spectrum, but the interesting stuff is what you can do with it. Here's a highway sign that had to be specially approved by the legislature of New Mexico. It's Highway 6563 in honor of the hydrogen alpha line. And these were a couple of spectra that I took when I was at San Fernando Observatory and just kind of scanning the sun at the time, partly for my own curiosity. And I came across, you want to see a red shift and a blue shift? You've got them right here. Something is going on here, I don't know what, where there was enough motion for it to be quite visible in hydrogen alpha, with one end being blue and one is red. I honestly don't remember which is which here, but there was something going on. In fact, I can tell you most likely it was the blue side is this side. But red and blue are, blue is down to the bottom, red is to the top. I'm pretty sure in this because it's a little darker. There's more gas coming to us. It's so absorbing it. When I went to the limb of the sun, looking all of this, this is just H alpha. Two things are happening. You'll notice that the line is narrow here and it broadens, and then you get to a bump. That bump is the sun's chromosphere with a temperature of about 10,000 degrees Kelvin. No, wait, let me get that. Yeah, 10,000, no, 10,000, yeah, 10,000 Kelvin. And that broadening is, the height is the thickness of the layer, and the broadening is the heating of it. But the sun itself in the photosphere even was warming up as it got higher. And then moving to a new spot as I scanned the limb, this appeared. And that's a prominence sticking out above the disk of the sun. Again, only seeing an H alpha. We're only seeing just a very narrow geometric spot on the sky, line on the sky. And there's even a little separation where there was very little material in that prominence. We'll see some prominences coming up though. If you happen to have an H alpha telescope, they're now much more available than they used to be when I got started. The thing you can do with many of them is to tune them. And I will just advise you to tune to the line center. Now, these pictures are a little contrasty, but the message I have for you is you will see the most detail if you get into the line center. And the way to get into the line center is to pay attention to how bright the whole field of view is. If the field of view is, if you can find the minimum brightness of the field of view, you're on line center. And that's where you want to be to see most of the detail here. When you get off the line center, and this is 2 angstroms, 20, no, I don't know. Can't do the arithmetic well enough, fast enough to do that. But this is well enough off the hydrogen alpha line that you can see the sunspots easily, and you can see faculae even there. Whereas here, they're just not visible. But here are some examples. Here's a prominence visible, which changes its character into a filament like this one when it's on the disk. You can see a sunspot over here, and you can see a brighter area. This whole magnetic region is active and could be flaring. Oftentimes it just looks brighter. It doesn't look flaring. When it looks like it's flaring, it does more. Here is again is a side view of a chromosphere and a prominence taken at a solar eclipse. This is full disk hydrogen, different dates, different examples, color, as you can see in H alpha. This is a really nice picture, actually, showing again a filament turning into a prominence over here, very dark, heavy filament here, active regions, filaments. The filaments tend to be the demarcation between different directions of magnetic field. So we might call it north-south, but we don't know which one is north and which one is south there, because it's not geometrically. We're just talking in terms of Earth's magnetic field. We're just asking, in one place the magnetic field is coming out from the sun, and the other it's going into the sun. So we could call it in or out, or we could just call it plus and minus. But usually you don't see it mentioned as north or south because we really don't know it. I also mentioned in passing the calcium K line. They used to be available K-line telescopes as well. I'm not sure there are anymore, but it was very interesting, and I got just a wonderful view through Webb's Daystar K-line telescope once with super granulation, which you can kind of start to make out here. It's much larger than the granules that you see, which are much smaller than these sunspots. And it was really intriguing to really make out all these areas of high magnetic field and activity, either in the black and white view here or in on a different date, the color view. But again, if you're of the age getting up there where your lenses are starting to cloud and color yellow, you lose your violet vision strongly. Having said that, they don't usually put north and south on charts. Here is an example of an active region where the magnetic field was measured. I don't believe they actually know what north and south is, but plus and minus would do just as fine there. And you see that there are field lines. You can even see midway here, you can see what look like iron filings, and that has to do with those magnetic field lines cutting across here. We can't actually measure magnetic fields like these, so this is not fantasy. This is just being able to measure it, and they laid this down for our edification. And then if there is a reconnection of magnetic field lines, we can get a flare like this. It goes from this is the hydrogen alpha before a flare to during a flare, and you can see what's happening. Those magnetic field lines are reconnected. The interesting thing, though, is even after seeing that, you don't see a big change in the photosphere, or I'm sorry, the chromosphere underneath where the flare was. So there are a number of things we wonder about. Here you can see, for instance, additional flaring. Sometimes here's a parallel pair of flares, and what we have is actually loops, coronal loops going across here. You can barely make them out, not real well, but here are some down here as well. And you can see what happens when things brighten up on the disk or near the edge of the disk. And here is, again, one of these parallel flares that would show as coronal loops if we could look down the aisleway between the two brightenings on the photosphere. Well, this is a picture that was taken with a H-alpha telescope from Coronado. There's a couple of manufacturers now that make these. And it looks nice, a little hard to see some of the detail, but if you want to look at, if you're taking pictures, especially if you want to see what you can do with that, use a PowerPoint occulting disk. And that's what I did. I just actually used a black shape that you can get with PowerPoint and just covered up most of the disk, and it's a much easier thing to look at. So if you can do that, And we do have instruments. Sometimes you can find them on available for sale from vendors. It's called a coronagraph. And a brief story on this. This erupting prominence is called Grandpa from 1946. It turned out to be so large that it expanded out. I don't have the whole series of pictures to show you, but it expanded completely out of the field of view. And so when they were building high altitude observatory in Colorado, the director insisted that they have a short focal length telescope that would be able to catch any more grandpas that might come in the future. Well, there haven't been very many of them, but I will have more to say on that. If you can find a commercial one, it's going to look something like this. It's the add-on down here at the bottom end. Since it goes on a refractor, it's got to have a right angle turn in it, and it does. Most of the H alpha telescopes you can buy on the market now also are refractors that they build this way. But the fixins on the inside are what matter. And in particular, there is a stem that holds one of several, you have to pick the right size, occulting discs that makes an artificial eclipse and re-images things so that by the time the image that is formed by the refractor on the front here and is blocked by this, allowing light only to go around the edges, goes through and is re-imaged, and eventually you get it out at the eyepiece and you get to see that. Or you put a camera on here and you can do the same thing. Actually, with this particular one, you can put the camera right on the end there. And so I had occasion to get one of these and had observed one of these big, heavy-duty, very complex, very black, very large sunspots, and you can just barely make it out over here. And I thought, I'm going to pull out the telescope just in case something interesting is going on. I'm in my back patio, and I set up the telescope, take one look, and this is what I see. Well, actually, it took me a couple of minutes to actually go and get the camera to put it on it, because there was no waiting for this. And I got the camera on, and boom, boom, boom.
Incredible.
It was. It just blew me away. I was late to work that day, and it was worth it, because I just recently realized I could put these together, and so I've done it for you. So you're seeing this for the first time. I project these for anybody. This is that same one. I had to rotate it 90 degrees just to get it into the same thing. And I have fitted the limb of the sun, or actually that's the false limb, that's the occulting disc, to match the occulting disc in the 1946 picture. So they're on the same scale. You can see the limb there. You see it connects to the limb there. You can argue with me if I got it exactly right, but don't bother. The important point to note is that this one went even higher than Grandpa.
That's right. That's great, Grandpa.
Yeah, yeah. I did later find that this one had received not so much the eruption, but the sunspot group had received a lot of attention in this solar physics community, such that it made it into Science News magazine. Then another time I was out teaching, showing the sun to a teacher's workshop up on Angeles Crest Highway, actually close to one of my usual observing spots that I use up there. And I saw this prominence, and those of the teachers that wanted to all got to see it this way as well. But I kept the telescope on just because. And I looked again. I was probably 40 minutes after I'd finished talking to them, and I'd gotten a picture, and look what happened.
Wow.
And there's just no telling what's going to happen. No, I'm going to go back here. Just notice the top end here is leaving. It is being ejected. This again is an erupting prominence. It's being ejected. But watch this. because it's falling back down. And I ran out of film, color film. So I reloaded, and you can still see this thing going on and on. Well, again, I had to see just how high it was going. And sure enough, it went a long way, not quite as high. Again, you can see how I matched the grandpa's occulting disc with this one, but I have slid it to the right. And you can see here's that segment that never managed to escape, or it's up here, the full size. And again, I rotated just to get it in the same orientation as grandpa. But overall, you can see that this was just really cool. And it was, if not as large, it was still pretty close. So these things do happen. You can also see in the extreme ultraviolet images that come from satellites now, sometimes they catch something like this as an erupting filament, or it'll erupt as a filament and eventually make it into the sky. So we do see these things, but it's still spectacular when you do. And it's not beyond the reach of instruments available to amateur astronomers like all of us.
Right. That's right.
So now I want to
Steve,
spend a little.
I hate to cut this a little short. We have Adam Block here. He's on a tight schedule, and he's our last speaker. Is it possible to split this presentation in two? We have more talks tomorrow afternoon with Fred Espenak.
Well, I'm almost done, Scott. If you can bear with me another couple of minutes, let me just finish off. We got 2 eclipses coming over the United States. A moon at perigee, total eclipse in April of 2024, a moon at apogee, annular eclipse in 2023, just a year away, folks, almost, well, 54 weeks maybe. And those paths cross, as you can see, from Oregon to Texas for the annular, and from Texas, San Antonio is very close to both paths, to all the way up into Maine in April of 2024. I strongly encourage you to go out and observe them. And this is just a quick listing of my advice to you, and make better astronomical use of the daytime if you have the interest and the time to do so. So with that, thank you for listening. And Scott, it's all yours.
Thank you so much, Steve. That was awesome. Okay. All right, Steve, thanks very much. Next year we plan to get you out here. So I think you're going to really enjoy it. Thanks very much.
Sounds good. You're welcome.
All right. Okay, so let's see. At this point, let me make some changes, and we will have Adam Block. Adam, you ready? Yeah, great. How about you want to?
Grab your mouse.
Here. Here's you.
So if I have a prop, is that going to be a surprise?
Show me what you got. Sure, it will be a surprise. You need a white screen, narrow screen.
Oh, for the prop. I'm just going to hold it on.
It's just going to hold. Okay, so it's going to be all right. Good.
So where do you want me to stand?
You can stand right there. You do. Put your mouse there.
Excellent.
All right.
You just tell me when to go.
I am going to introduce him. Adam Block is, you may have heard of Adam Block over the years, but Adam is, if there is a Ansel Adams of astrophotography, certainly Adam Block was one of these people. And there was once upon a time I was going to be a zone system artist photographer, and I corresponded with Ansel when I was a teenager. I met many master photographers from the Bay Area back in my teenage years, and so I really appreciate the craft and skill and real hard work that it takes to get beautiful images, and I recognize people who are masters of their craft. And Adam is absolutely one of these people. But beyond that, Adam has worked very, very hard for decades, not only to teach people this craft and to elevate their skill, but he's used his images for outreach. But this outreach thing goes beyond his images. His programs at Mount Lemmon, at Kip Peak, are just two of his signature programs. He's done many, many things to help organize, formal educational outreach programs. And, if there's anything that Adam, he's so famous for his images. He puts an image up on social media and blows really everybody away. That it kind of drowns out the importance of the outreach work that he's done. And I'm really happy that Adam's here. He's taking the time out of his very busy schedule to do it. And so, Adam, thank you very much. Thank you.
So first a correction. The only thing I have related to Ansel Adams is the ADAM in the name. That's about it. But I appreciate that introduction, and it certainly segues very well into what I want to talk about today. Is my screen going to?
Not yet, but it will be short.
Okay, good. It really is a great introduction to the other side of what I've done, which is the public outreach side of astronomical endeavors that I've undertaken through time. So I'm calling the title of this talk, The Human Equation. And this talk, unlike maybe others that you've been listening to today, is more anecdotal. It is more an experiential kind of talk rather than one that is, dealing in numbers and things like that. But I would claim that I have good reason to be able to speak with some expertise on it because I've spent an awful lot of time doing it. And as Scott mentioned, there's the Kip Peak program and the Mount Lemmon program that I'll be talking about here in just a moment. But all of these presentations, what they basically were, are things that are going to be unfolding perhaps here, tonight when it's dark, which is to look through a telescope visually and see stuff. And anyone that's done that, and I assume that everyone in this room, this is what you do, knows how challenging it is to get someone else to look through a telescope and see things well. And then once you've done that, be able to explain what it is that they're seeing, why it's interesting, how it is connected to everything else around them. So those challenges are the things that I undertook in the course of making these public outreach presentations. In fact, I was honored and privileged to spend that kind of intimate time with people. It may have been their first time to have that opportunity to look through a telescope and see a planet or a galaxy or something like that. So as I mentioned, let's be sure this will, is it actually?
Yes.
It is?
Oh,
okay, so now I know the distance. It's the distance, that's fine, I'll walk over. I'll walk over there. So my time began at Kip Peak National Observatory after I graduated from the University of Arizona. It just so happened serendipitously, the visitor center was going to create a new public outreach program. They were going to install a telescope at the visitor center from which they would offer what I would call real public outreach with the right kind of intent. Most professional observatories, they might offer, as Kip Peak did, they would offer an evening presentation of some sort where the public would be able to go up to one of the professional telescopes and to look through it, take a peek through an eyepiece where reluctant astronomers would give some of that time for that opportunity. And there might be 50 people in line who would stand there, cycle through, look through a telescope for a moment. An astronomer might say something clever, and that would be an experience. And I don't think that that's the most effective one. And these presentations that were given at Kitt Peak, I think, were more along the lines as I developed them, being that kind of experience. These were multiple hour long experiences, really intimate. They were inquiry based, hands-on, and hopefully memorable in a way that was educational and fun. And so it's these experiences that I really got a lot of information on. Oh, because there's a delay. Did I just raise your finger if I did it? Did I change it? There we go. Okay, now I understand. So this is one of the telescopes. It's actually one of the later telescopes that was used. It's a 20-inch telescope. There are a number of telescopes. They are still using these telescopes today at Kitt Peak to do these presentations. How many people in this room have actually participated in either the Kitt Peak program or the Mount Lemmon Sky Center program? Well, that's not a lot of people. You guys got to go do it. Oh my goodness. Okay.
Is Kitt Peak back up?
Yeah, well, that may be a problem today, but I'm talking in the ideal world in general, that these programs should be available. How about that? Okay, so this is where I need to start.
There you go.
Okay, got it. So these presentations, then I said, as I mentioned, they began with actually something that Scott will be familiar with. An LX200, 16-inch LX200 on the right is what the program began with, and then proceeded with some other telescopes in the future. By the way, that LX200 in that day, this would have been in 1995, 1996 when it began. Not really a great telescope, certainly not for astrophotography. But in the day, it's just not made to do this kind of thing. And so with the progression of some of these other pieces of instrumentation really, really helped. But as I say, I spent a lot of time with people to do this. And I really do feel that I shaped public outreach, certainly locally here in the Southwest, as part of doing these kinds of presentations. I calculated once how many people over 20 years I spent an evening with, hours long evening. And I think no less than 60,000 people. It's between 50 or 60,000 people. That's a lot of people. That's enough people that you learn things about people. You learn what their expectations are. You learn how they interact with a telescope. You learn what their misconceptions, their conceptions are, perspectives, all kinds of things. And the things that I really found interesting were the ones that were cross-cultural. Didn't matter where you came from, everyone seemed to do certain kinds of things. So proceeded from Kitt Peak to go to Mount Lemmon. I should just say why. It is still true today, by the way, the statement is the National Observatory really didn't want to expand the public outreach program in a way that I thought was either valuable or necessary. I mean, they wanted to have a public program, but not in a way that I thought could be bigger and better. So I moved on, and I found someone that would donate a telescope for the cause, convinced the university that they wanted to have this kind of public presentation, these new kinds of programs on top of Mount Lemmon. I'm going to go back here. I don't know if it goes back or not. So I worked at Mount Lemmon, and if you haven't done that, it's a great program. It has a 32-inch telescope, a 24-inch telescope. You can go up, you can look through. It's the best, I think, program of its kind, especially in terms of the philosophy behind the way in which you do it. And I'm just going to hint at a few of these things now. I'm going to be talking about my experience with getting people to look through telescopes and appreciate what they got to see as part of these experiences. Right. Okay. So part of the lessons that I learned began before these presentations, these programs. It began at the University of Arizona, where I ran the campus station telescope for undergraduate students who had these general education requirements where they would need to take a course. If they weren't in sciences, they need to take at least a science course. And some of these students elected to take astronomy courses. And one of the assignments is to go to the telescope and look through it. That observatory there has a 21-inch telescope. So the students had to go on one evening and look at a handful of objects where they would sketch what they saw and then have to write a little bit about what they were, these things that they saw on the telescope. And our job as operators of the facility was to make sure the students could see the stuff and they had a reasonable time completing their assignment. So at this telescope then, I had a number of experiences, but the one that is most memorable is I had a young lady come to the telescope. We were pointing at the moon. That's the telescope there. It's still, this is a very nice photo op of a famous astronomer, but it's actually what the telescope looked like back when I was using it. And this young lady walked up to the telescope. You know, I asked her, could you see the moon? Can you see the moon? And she said, yes, she can see the moon. But what I took note of is that I could see the image of the moon on her forehead. So I knew that she was not seeing the moon, right? The light from the moon was not going into her eye. Now, I'm not going to challenge her. The way that it works here is that many of these students are not just disinterested, but willfully disinterested, in that they want to be at a party, they want to go to the football game, they want to be somewhere else rather than looking through a telescope. That's fine. But I learned from it. And one of the things, a simple observation, I mean, it seems simple, but you really got to pay attention to it, is that when you show objects bright, like the moon, you can use that as a tool to know whether the light is going into someone's eyeball. Very, very useful to know, right? But not all things are going to be that bright. It won't necessarily be that easy to tell if someone is able to see something through a telescope. So you have to come up with some tricks, some ways in which that is going to work more effectively. One of the things that I found absolutely critical for the success of the programs that I generated is that they all started in the daytime. How many public programs that are formal presentations do that? At the time that I created these programs, I don't think anyone did. And I do think that it's absolutely critical for success. Most people, when they called on the phone to make a reservation for the program, the first question that they asked was, why do I have to be there 2 hours early? What are we going to be doing? It's not dark for another 2 hours, right? And the answer is, I'm going to have an opportunity to show people how to be successful later on. I'm going to be able to explain all kinds of things about the telescope. I'm going to give people an opportunity to feel what it is like to succeed in advance of the evening. And one of the ways to do that is, of course, to explain how to use an eyepiece, how to look through an eyepiece. And, you know, most people would say, well, how hard could that be to look through an eyepiece and see stuff? And the answer is, after 60,000 people or whatever, surprisingly difficult. The first thing I need to explain to people is that, you know, you need to align your eye and look through the eyepiece directly. If you don't, you're just going to see blackness. And in the dark, it often happens that people, not only are they looking at some odd angle, may literally be looking at the side of the eyepiece. And that, of course, is not helpful. So one of the most important keys that I tell people to do is to, let's go one more, is to do this trick of grasping the eyepiece. In many public presentations, people are afraid or maybe even told not to touch the eyepiece. That is counter to success. One of the things that you want to take advantage of is the fact that even when we close our eyes, we know in space the relationship between our body parts and where they are. And you know where the center of your hand is, so that in the dark, if you grasp the eyepiece, you can more easily guide your eye up to the right place and see whatever it is you need to see, from planets to other galaxies. So in all of my presentations, that was a very important and critical part of the success of the program. By the way, people that, another thing that I would tell people, they often end up too far away from the eyepiece. So I would instruct people that you need to be as close as letting especially if you have a rubber guard here, let the guard brush, you know, the side of your nose or your eyebrow. That's close enough. Press your glasses against it, or if you're going to remove your glasses, then you can get up to that good distance to see the full field of view. People often are too far away. That, of course, leads to another topic entirely, but I want to, which is the focus problem, and I'll get to that in a moment. But there is this other thing that happens, which is that you still, even after you've explained how to guide your eye up to the eyepiece, and you're having some success. In the daytime, it's easy to do because you can see the light literally coming through the eyepiece. So when people guide their eye up and they get to see something, a star, a planet, whatever it is, now they have some success, right? But there are always going to be people where it's, you know, later on, it's just not successful. And you want to take their heads and you want to say, look, this is, you know, you can't do that. There's just no way to do that. So what are you going to do? Well, one of the things that I learned is, again, from the moon and later from the daytime sky, what if I could make light come out of the eyepiece? One of the nice tricks that you can do is that you can take, I'm guessing what my next slide is, you can take a red flashlight or a dim flashlight or something like this, and you can shine it down the center of the telescope. And in doing so, what will happen is the people will see light coming out of the eyepiece. It will be dimly illuminated in such a way that they can guide their eye up to the eyepiece. And then once you've done that, you remove the red light. And then they see what they should see. And that trick I've never seen done in a public presentation. It should be done by everyone. It's easy to do. It's easy to get someone to align their eyes in that way. And then they'll be able to see. I mean, I could show the faintest things I wanted to people once they had their eyes, basically in the right spot. And I knew that it was in the right spot. So that's a cool trick that I hope people will take away from this talk. Now, there is this other problem. The other problem is there is no problem if you have two people at your telescope. And, everyone can look and fiddle, and there's no problem at all. Problem is when you have 20 to 30 people in line at a telescope. Now, what are you going to do? People's vision are different. People see things differently. And so this, again, really highlights the need for having a program begin in the day. Because what you can do in the day is you can show objects through the telescope in the daytime sky, including stars and things like that, which, I'm going to get back in here. I'll come back to this one. Stars and things like that, which give people this opportunity to focus the telescope. Let me just go back to this slide because I think Scott will appreciate this one. This idea of managing focus at a telescope is truly critical. It is absolutely necessary. You can damage your telescope and stop a public presentation if you don't explain it correctly. It literally matters. So this is the focus knob of the 16-inch LX200. And if you look on the left there, you can see that when you pull it out, it has at the end, there's a little hole in the steel bolt, which attaches to a pin, goes through a pin that attaches to the primary mirror. And as you turn the knob, it moves the primary mirror in and out to focus. But then if you remove the outer covering there, you can see that the steel bolt passes through a brass coupling that's threaded on the inside. And also note on furthest to the right that there is a hard stop. There's a limit to how far you can turn, obviously, so that it is possible that if you turn the knob and you reach the hard stop and you can continue to turn, that brass is a softer metal than the steel. And so what you do is you completely take all of the threads out of that inner coupling and your program is done. Now, the reason that this happens is because you didn't explain, I didn't explain, what it means to be in focus. Being in focus has nothing to do with not seeing something in an eyepiece. In other words, people will sometimes look through a telescope, but they don't see anything and they go, I'm not seeing anything because the telescope isn't in focus. I'm going to keep turning the knob until I see something. That is an infinite bad loop because they will never see anything as they turn the knob if they're not aligned. So the key thing to say to people is that in focus or not, you will always see light coming out of and through the eyepiece. If you don't see anything, don't touch the focus knob. You need to worry about the alignment of your eye. So that was the key. And I know that Scott won't remember this, but I made many frantic phone calls. I can't remember if it was once or twice that this happened to me before I learned that I needed to have backup knobs so that I could, it's only like a 5 or 10 minute fix to take off the old one and put in a new one, and I'm golden, right? It might have taken me 2 times. I just couldn't believe this could happen, maybe, kind of thing. But then I called Mead and I said, you guys have to send me these things fast and now, and I need backups and everything. So that was a thing for me. Okay, so the other part of the focus endeavor is that when you have a large group of people, here's how I think is the best case scenario. So I show something, let's say in the daytime, so I can figure this out in the day. I show a star through the telescope in the day, beautiful twinkly star. What's cool about stars in the day, their color is even better sometimes than it looks at night against that flat blue sky. But I can tell people that an in-focus image of a star is a nice sparkly ball of light. Through the telescopes I was using, if it's out of focus, you would see a donut or a Cheerio or something along those lines. You wouldn't see the kind of thing that I was describing. So the first thing I did is I had everyone look through the telescope, no one touched the focus. Just look. If you're seeing what appears, what I've described to be as out of focus stars, the second time around, I let everyone go ahead and fiddle. The problem with making the adjustment in the beginning is that you're guaranteeing that when one person makes an adjustment in the beginning, everyone else has to make an adjustment thereafter, because everyone's vision is potentially different. The worst case scenario, by the way, is at a public program where you're not managing focus. Someone makes an adjustment at some point because you're being kind. Yeah, go ahead and make an adjustment. But then the next 10 or 12 people that look through the telescope either don't know that that isn't how things should appear, or they're too timid perhaps to make the adjustment. And so now you have 10 or 12 people who have looked at, I don't know what they're looking at, out of focus images of things. It's terrible. It's not how public outreach, you want to minimize frustration, you want to get the very best results you can. So that's not how to do it. So after I have everyone look, now people can try to adjust the telescope. Those people that actually had vision that's my vision perhaps when I used the telescope was average, right? So on average, there's going to be a good fraction of people who saw a nice, small, sparkly ball of light, and everything's good. There are going to be people who are fiddle curious. They saw a small, sparkly ball of light, but they're going to still want to see, is it really as good as it can be? They get to fiddle. And what they'll learn is that, hey, you know what? Adam's vision is not that bad. I'm going to go with the way that he has it, and it'll probably be fine. They can still revert to fiddling if they want. And then we're going to have the people whose vision is significantly different, and they're going to learn how to adjust the telescope so that they can focus for the rest of the night. And now what I have here is I have a group of people who are just going to look through the telescope because they're happy. I'm going to have the fiddle curious people who are now taken care of, and they can still convert if they're still not satisfied. Well, maybe Adam didn't focus this one very good. And I tell anyone that wants to make an adjustment to always be at the end of the line, to just let everyone's going to get a chance to look. That's what these programs are built on. Everyone gets to see the thing, but those people that want to adjust be at the end. And then I have avoided the situation of the people that don't want to touch the telescope not getting a good view on average, or the people who, that someone's going to make an adjustment at the beginning, and then I go look at the end and I say, oh my God, what are these people looking at? That's terrible. So that is a great way, I think, to deal with the focus issue, if you will. Another element of human stuff is what people see when they look through the telescope. Now we've got everyone aligned, right? And the image is in focus. Now we have to deal with their brains and their expectations and what it is that people see and don't see and all kinds of stuff. There is, I think that this topic I'm talking about could actually be a book. So I'm only highlighting a few very special parts of this. But planetary nebulae are great to show in a telescope, especially when you have a 32-inch telescope atop Mount Lemmon at 9,000 feet. These things, they scream blue-green. I mean, they are just beautiful, luminous balls of color in a telescope. No question about it. As long as you can see color, these things are colorful. And yet, when an adult looks through a telescope, they don't necessarily see color. They go, does that have a color? I can't tell what color that is. Or worse, they'll say it looks red. I'm like, it can't be red. So children, on the other hand, always get the answer right. It's amazing. And it's not that that there's this big difference between children's eyes and adults' eyes. That's not it at all. But when I ask a child, and I don't lead them, and I'm not trying to make it so, I ask them to look through the telescope. I ask them, do you see the fuzzy thing in the middle? And they say, yes, I see it. And I ask, well, what color or colors does it look like to you? And it's amazing, generally, especially girls, they will say, it looks blue or green. I can't tell, it's blue or green. They will literally say both colors. And it's fantastic. And I say, you're exactly right, it is blue-green. See, they don't know the word for teal. If they knew the word teal, they would have said teal, but they don't know teal. It's blue-green, it's what it is. Absolutely perfect. The funny thing about young people is that young enough people, because they are accustomed every day to being surprised and seeing new things, they're not surprised to be surprised. So it's actually hard to impress young people who are constantly bombarded with things, they haven't seen before. Adults, however, who have seen an awful lot of stuff, it's hard to, claim I'm going to be able to show you something you haven't seen before, right? Although looking through a telescope, that is actually the case. And part of the problem that people have or don't have practice with is turning off all of the stuff that your brain wants to do to fill in information, expectations of what you think you're going to see, what you actually see. Part of the skill set of a visual astronomer is to be able to only accept what the eyeball is giving them without reservation, just as if it's a little camera and it is showing you something, then to turn off all of that activity in your brain. That's very hard to do. And so doing that then is that skill. One of the funny things is that, I would often struggle with some faint objects to get people to see them. Even after explaining about averted vision and all the physiology of the eye, we got that covered. So I would tell people, look here, do this. I can't see it. So I'd ask them, please come back. And I would try some other method. Look at the star over here on the right. Don't look at the center. Just look at that star, but glance at the center. Do you see? Oh, I see it. I see the cloud, whatever it is. And then I ask them, why didn't you see it before? And the answer is because I didn't know what I was supposed to see. That's always the answer. What was I supposed to see? You're not supposed to see anything. There's no suppose. Suppose is that filling in. It's that expectation of something. And it's that counter to the skill of turning down the mind to be able to just accept what the eyeball shows. Yeah. Oh, well, that's a whole other thing. So, as part of the public presentation, I have an opportunity to explain about how detectors work in astronomy, because I'm going to be showing them pictures later on, my beautiful astrophotography, right? So I explain how sensitive these things are compared to our eyes. They have a chance to compare. I will show them pictures taken through this telescope compared to what they see with their eyes. And then you can maybe take that other step. Well, here's what a space telescope can do above the blurring of the Earth's atmosphere using the best instrumentation possible. So as part of a public program, you can get them to reach those steps. It's harder without having that visceral experience of looking through a telescope, but I think it's a great way to make those steps and make headway to answer questions like that. And there is a final thought that I'd like to have here, because I want to go another direction. I was just talking about these kind of elements of stargazing programs, but I've also spent time with thousands of people doing what I would call, astrophotography, either workshops or instructional things. I answer all kinds of questions about astrophotography and image processing. And there are some common themes when it comes to the processing images, but specifically in the interpretation or appreciation of astronomical images. And I have my own little theory, kind of, about why that is. And I think there is a why. I think it demands a why. I think there's an actual real question there as to why these kinds of things happen. So one of the things you'll note about amateur astronomy, you'll see pictures like this from beginning images, where almost always someone who's just starting out will try to process their image, and they make the sky very black. They make it so black, it's black clipped, that it is literally removing some element of the information that they have contained in their data. So here's a picture of the very famous Whirlpool Galaxy. Here's another picture of the Whirlpool Galaxy. You can't even see the outer arms now. It's just so dark and high contrast. And here is another image of a Whirlpool Galaxy from beginning. But this always happens. Why is it never the other way? Why don't we have people that do low contrast images where they make a very bright sky? Why not that? Why not random amounts of both? You never get that. You always get this. I think that's a question that needs to be answered. Why? Why is that? So one of the things that inspired me to think deeply about the way in which people look at astronomical images was inspired by this philosopher. His name is Dennis Dutton. And he had a theory of why people find things attractive or beautiful in some manner. And he was an art, this is an art philosopher in particular. So why are some pieces of art deemed better or in some way more beautiful than other things? But this also applies to the natural world around us. And I'm just going to give you the highlight here because this is a whole nother talk. But the idea is that there are things in our evolutionary past that still in some way impose preferences today. People just naturally have particular preferences that are driven by an evolutionary heritage. And I will just literally read his quote because it's a very good one. It says, "Is beauty in the eye of the beholder? No, it's deep within our minds. It's a gift handed down to us from the intelligent skills and the rich emotional lives of our most ancient ancestors. Our powerful reaction to images, to the expression of emotion in art, and to the beauty of music, and to the night sky," I underline that, "will be with us and our descendants for as long as the human race exists." And it's the night sky appreciation that I find particularly interesting, especially as it relates to the appreciation of astronomical images. So let me show you a few more astronomical images just to drive home this point. Here is a picture of the Eagle Nebula, pretty dark looking thing. And here is another picture, another dark thing. So, did it come up? Okay. There it is. So why dark? Why dark? I think it's dark because it actually echoes what we see with our eyes when we look at the sky. What we see with the human eyeball sky, that archetypal sky image, if you will, is what we expect in astronomical images. And it's more than just high contrast. It is also literally the sizes of the stars themselves and the number of stars that you might see. And that affects the preferences as to what people deem as beautiful in imagery. But where does that come from? That doesn't answer, just looking at the sky doesn't do it. So for me, I think it is likened to one of Dennis Dutton's theories. And it's this amazing fact. People cross-culturally around the world have a preference for landscapes. If you type in Google, beautiful landscape, and you look at all the pictures and paintings that are presented to you, they look very similar. They will have very particular elements in them that include, usually there will be a small stream or water. There'll be low lying grass with not too many trees. There will be some trees, but not many, because you want to also be able to see to the horizon. And all of these features in this landscape, this preferred landscape, is the features that keep you alive, actually. You want to be able to see far away because you want to know if there's a threatening cloud or there are animals coming to get you. You want to be able to climb up a tree if there is something that's chasing you. You want there to be water so you have something to drink. The landscape out here is beautiful, but it won't be preferred if you make a picture of it. What's preferred is the one that was available to our ancestors on the, in the Pleistocene era, on the African savanna. That's a beautiful scene because evolutionarily it benefited us. In the same breath, I would say there's something very special about the night sky scene because people were seeing it. And the reason they were seeing it is because at night, we are hypervigilant. Literally, our physiology changes. We have different kinds of bodily changes, the most obvious being our eyes. In the dark, we produce rhodopsin, which increases the sensitivity to the cells of our eyes so we can see more of the world around us. But there are also other physiological effects that undergo in the nighttime due to certain rhythms, as well as literally being in the dark. So this state of hypervigilance means that if you're in the dark and you're one of our ancient ancestors and you're looking around making sure you're trying to stay alive, what is the only thing that you see? You don't see the trees very well. You don't see your friends very well. The only thing you see well is the night sky. I think that somehow ended up in our heads, that night sky view. And I think that it's still with us today, and it affects our appreciation of astronomical imagery. So now let me finally show you another example of this. So here's a picture of the Pleiades I took with a modest sized telescope, so it gives a large field of view. The Pleiades, a star cluster. So you have all the beautiful stars. You can see some of the nebulosity, right? One of the interesting things today in astronomical imagery is that there are now very fancy algorithms, especially neural networks and AI kind of algorithms that you train in order to be able to identify stars from non-stars. And so you can process your image in this way by removing the stars and making a guess as what would have been there instead of stars. And you're left with this beautiful field of all of the dust and gas that's within there without the stars, right? And so you might think, well, this could be a beautiful picture. This actually shows all the cool, without the stars, all the cool dust and gas and stuff that's in the region. This tells a very interesting story. But when you put the stars back, right, you have a different story. What people really want to do is they want to put the stars back a little bit, not so much. So let me show you another, because this could be what people favor. Why didn't we go this way? Why aren't we just removing all stars from our pictures if we want to show a nebula? And that is a thing, by the way. Nowadays, when people use, especially from their backyards, they're all doing narrowband imaging. That's the one way you can make your sky dark. So you take pictures of nebula. Guess what you don't have a lot of when you look at narrowband imaging? You don't have a lot of bright stars in the continuum space, right? So you get that natural kind of view, which is why it's very much preferred. But here is a picture of another nebula out there. And once again, we can remove the stars from them. But the cool thing is there's yet another algorithm that you can employ once you have a starless view and a view that just has the stars. I'm not showing that, but you can get a star-only image here once you separate the two. And then you can change the stars if you want. And then you would add the stars back in at some other level, right? So this level here is the original level, and then this is the level here. It's hard to blink with this. Did it change? Oh, it didn't change? Sorry. Oh, now it did. So now I have to go back, right? Yeah. Sorry.
Let me try.
Yes, could you go back and forth between these two?
Previous.
Go to the previous one. That's right.
I'm gonna blink a well, but.
Just go back one slide. Okay. There it is before. Okay, now let's go. Now let's do after. The whole point that I want to make is that, yep, there is a very particular amount of stars and size of stars that you'll see everyone prefers. And that preference, again, I think is an echo of this preferred kind of night sky archetypal view that we might have from an evolutionary kind of memory of a preference of sorts. So that's what I wanted to demonstrate. And then I will end the talk on what happens to be one of my most recent pictures, which is a narrowband image. I got some data from a friend who allowed me to process this. This is the Rosette Nebula. You can see that, again, it's a minimization of stars because in narrowband, you don't see that many of them. And on a final note, because I am standing here now at Oracle State Park, one of the things that is in play is perhaps the opportunity to get this particular telescope. There it is. It is still in a box, it's in storage, and it is my hope that it will become a feature here of the Oracle State Park, perhaps sometime in the future. That is the hope, and so it's something that we're working towards. And with that, I want to thank you very much for giving me the opportunity to talk to you today about all of these things.
We started working with Adam here at the park in 2019, I think it was. We're partnering up with the University of Arizona to have an observatory here at the park. The intention for this observatory is going to be certainly public outreach, But when we're not using it for public outreach, it'll be used by the students and the professors at the university because it will be a research grade telescope and observatory system. So I want to thank Adam for all of his dedication and support for what we've been doing. We got, of course, derailed a lot because of COVID, but we're starting to get back now on track. He has that telescope that we're sort of targeting to come down here. Once we know that's all in place, then we move to the next steps of getting an observatory design. It's a potentially full-blown science center, and we're working with the university to make that happen as well. And Adam is our primary point of contact because of his work with KITFI, because of his work with Mount Lemmon Sky Center up there. He's the perfect guy to make that observatory happen here at this International Blair Sky Park, Rubin State Park. So thank you, Adam. We do appreciate it.
Okay, thank you very much. Thank you, Mike. Okay, everyone. Well, that wraps up today's speaker series. Tomorrow we have a birding event at 6:30.
6:30, I think. Show up by 6 anyway.
Show up by 6. Okay, all right.
Anybody who's wanting to go has an email for reservation. Okay.
And where here at the Cannerly Ranch House?
Yes.
Okay, all right. Okay, and then we have for everybody here that got Biosphere 2 tickets, so it's a good time for you to go see Biosphere 2.
It opens at 9.
Mhm.
Do you think a lot of people will be going? Will it be in groups or are we just kind of on our own?
You're kind of on your own. I really did not know. We did not know when people really wanted to do this. So, everybody had their own individual schedule. Some of you are camping, some of you are staying in B&Bs around here or hotels. So we just wanted to work with you on that and let you set your own schedule.
And they do not do it guided, self-guided. So when you get there, you're gonna see a thing with a QR code that's gonna tell you to download the app. So they'll, as you walk through it.
Right.
Guide you.
Biosphere 2 is literally 10 miles away from here. So
It's about 10 or 15 minutes, but then that's where it hits the highway, and it's about another 7-10 minutes to get in.
get back up in there. Okay.
And it's a long walk up.
Right.
Do
Right.
they have Wi-Fi?
Biosphere? Yeah, as far as I know, they
They
do.
do that. Yeah, that's how it's a self-guided tour.
Yep. And then they have an app, of course, that you download. At 1 o'clock, Fred Aspenak, Mr. Eclipse, is going to be on with us via Zoom. And then we have David Eicher, editor-in-chief of Astronomy Magazine. He'll be on with us. And then we've got Brandon Hamill, who will be coming and in person giving a talk here. So that kind of wraps that up. And then you guys are hopefully getting some clear skies at this point and constructing some astronomy. Those of you who want to do astrophotography, we have a group use area that does have power down there. So if you want to be down there, get in touch with one of us and we'll make that happen. Okay, all right. Well, at night you can come and go. A lot of you are not staying in the park. But you can leave your equipment set up. It's relatively safe, we are basically have taken over the park, okay? And, but if you're staying in a hotel or one of the bed and breakfasts around here, you can get in and out of the gate, okay? Just make sure that you have your pass.
Maybe don't say while you're still broadcasting.
It's okay. You can still get, yes. So I'm not going to tell you how you can get in and out of the gate, okay? Live, but anyhow, yeah, you can. We actually told them yesterday. So, right. But we'll catch you on the way out and give you the secret on how to get in and out. The main message is you're not trapped here. Okay, a lot of star parties. You got in, you ain't getting out. Okay, so that's a little bit different here. And then on Friday night, of course, we start to have the events happen at the individual businesses. So there's going to be music and drinks and food. You know, of course, you'll be paying for the drinks and the food, but they're supplying music and a telescope. I'll be at one of the events myself. The Tucson Astronomical Association is going to be out there in force. Starzona is joining up with us as well. It's going to be a lot of fun, you know.
If you
So
want to be out there with one of your telescopes, or just your binoculars,
Yeah.
or just your voice,
yeah,
your education, your
yeah,
knowledge.
and the whole community knows about this. So it is going to be sort of an outreach type of event. So you got some cool tips from Adam Block on how to make that more successful.
Bring your latest.
Right. And then Saturday night, we come back here and we're gonna have music, and it is for the public. So
Geology talk at 11, I think it is on Saturday.
when is the bad experience again?
Okay, so the geology talk in the morning, 11-ish.
This is Saturday.
Hike down on the trail, then there's gonna be people around the patio area here, other different things in the afternoon. Then at 5 o'clock, I think it is. It's on the schedule. It's on the schedule, whatever the time is. So take a look at the website, use the QR code back to bed. But there's gonna be a bat talk. They're gonna take you out to a bat line, basically. And I did this a few years ago. If you wanted to, you could pet a bat.
You can pet a bat.
People did.
I don't know if they let you do that anymore.
So that's an awesome experience if you've never done something like that. Also, we're gonna be out in the wildlife line with some night scopes that Scott has brought to the company. So you'll be doing some of that.
Yeah, I have night vision, thermal, like not just night vision, thermal imaging. And we'll be out on this pavilion out here. So
So basically, we're advertising the star party back up here in the patio area and extending out the walkway. Be from 6 to 9 or 6 to 10, whenever people wind up doing that. And again, local astronomy clubs are supporting it, Starzona is supporting it. But if you all want to come out here.
oh yeah, and the Saddlebrook stargazers are going to be there too. So we want to thank all of them.
Local astronomy club, that's what supports.
Yeah. So all these restaurants, local, even the Ford dealership has been supporting this. So this is part of the cultural festival. On Sunday, we're going to be giving away door prizes. So you're not just going to back up and split, because you've got artists who have donated art for it, okay, which is cool. And we have some stuff from Explore Scientific that you could win as well. So
And that's at the Oracle Community Center, starting at 11.
11 o'clock.
Real short. The community
Yep.
center is going to have food there for us.
No, they're not. They decided that they were afraid they were gonna be left over, so now they decided not to have any food.
Okay, thanks. I hadn't got that up. Yeah. Okay. But yeah, be there for the door prizes.
yeah. And we've been trying some of the different areas, restaurants in the area, and it's pretty good. So decent. Yes, sir.
Saturday night.
They're not going to use your scopes.
It's here at the.
Yeah, it's at the Kennedy Ranch House. So if you want them to use your scope and you want to participate in that outreach, by all means. For some people, they love that. So, yeah.
Don't feel obligated.
no, this is you guys have your own private thing. That's what you've paid for. But we want you to
There's going to be.
engage with other people and have
At
fun
least a
too.
24-inch
So
stall, I've been told. There might also be a 20-inch stall up there, as well as some other stuff, so. Piece of neat stuff.
yeah, and for those of you who haven't tried the Unistellar or EV scope, I'm going to have one, so you can try it out.
Very
Okay.
impressive, right? We had a star party here, the last star party we had here in, this is amazing. One of the club members got one of those, brought it up here. It was great for public outreach.
Yeah.
You know, there are some people with scopes that are using them to.
To look at what?
Satellite streets.
Satellite streaks. Okay.
It's turning out very well.
Huh. Great. Good. Well, thank you very much, everyone. Thanks for all of you that tuned in on our live stream. And we will stream the talks tomorrow, starting at about 1 o'clock. Thank you.
I don't see anyone. My wife. Yeah.